products to the market. The advantages of omnidirectional vision is quite obvious. With less camera devices, we simply see more. This fact becomes clear if we, for example, as you see it on the slide, consider an indoor monitoring task. An omnidirectional imaging device allows me, for example, to observe a whole room, a whole inner space with one single camera device. By means of standard vision, we would have missed 3 persons in our example. Using modern AI algorithms, I can now create powerful applications. In the recent years, 2D image processing becomes more and more augmented by the third dimension. The victory of so-called depth cameras actually began in the consumer market, and now it's conquering the industrial environment. The measurement result is no longer just a flat image. It is a 3-dimensional point clouds, giving a spatial information to each and every pixel. The 3D cameras simultaneously provide X, Y, and Z coordinates in physical units. But the most important thing is that 3D data makes our machine vision algorithms, our machine vision applications more robust against environmental changes or even immune. For example, if the distance of an object that you want to measure will rise from the camera, then your algorithms get more immune if you use 3D data. We believe that the combination of omnidirectional imaging, 3D perception, and neural network-based scene analysis forms a powerful approach to create intelligent machine vision solutions. So perceive a large area, locate everything, and find out what's going on there. Our team at 3D Vision Labs had the idea that as many developers as possible should be able to realize such applications. So the idea was born to realize the right 3D camera for it. We call this HemiStereo NX. HemiStereo NX is a compact and robust 3D machine vision camera, ready for driving AI-based applications. The camera is equipped with 2 high-resolution imagers and an internal processing device for realizing real-time stereo vision-based distance measurements. But the craziest feature is its huge field of view of 180 degrees in 2D as well as 3D. On the right side of the slide, you can see some sample data. The distance information is provided as color-coded image, and you see the large coverage area of the camera. If you'd like to learn more about this, we have made a special webinar for this. You can find the link down below on the slide if you are interested. Here we see some exemplary data made by the NX. It shows a high-resolution 3D point cloud that was made by a one-shot recording of an historic old town. In other words, what you see is just one single frame. The red pins on the bottom of the slide mark the camera's position, which helps to comprehend the vast field of view of the camera. It's really cool, isn't it? However, we believe that by means of this technology, we can realize a vast variety of future applications. For example, we think that the private and the public spaces in future will turn into smart environments. These spaces will somehow interact with us people that are present there. They will turn into intelligent service providers. Intelligent spaces of the future will perceive and understand the situation of people that are present in the scene. And they will understand what are the needs of the persons. By means of intelligent cameras, we will be able to realize new services for building application, for communication, and for entertainment. So our buildings of the future will be more safe, more secure, and they will be more comfortable. Over the past few years, 2D machine vision has become a vital part in industrial automation, especially in classical applications like quality control, for example. Now, 3D machine vision is coming up, and it has the potential to change entire industries. I think also at this place, the future will belong to intelligent, to seeing devices. For example, statically mounted sensor networks in a complex production environment will record and will generate a lot of data, for example, for process optimization. They will monitor excess stocks. They will recognize unnecessary walking routes of workers. Being mounted on autonomous or, for example, assisted vehicles, such devices will generate data, for example, for navigation applications. They will generate data for collision avoidance, and they will perform intelligent object recognition. All of these applications, all of these vision solutions can benefit from a large field of view. To make such applications come true, there's a lot of work to do for the developers. There's a lot of work to do for us. So we have to collect the image data. We have to process it with the right algorithm. We have to develop the algorithms themselves. So we have to generate a lot of high-level information for the application that is above it. This can be on the one side, as you see it on the slide. This can be navigation data for HEV positioning as a result of a SLAM algorithm. This can also be, for example, detected people in an image. And finally, a 3D map of all the people present in the scene. So now we have omnidirectional 2D data, we have omnidirectional distance information, and we have magnificent algorithms. What's next? Are we going to process all this data in the cloud? I think we should pay special attention to the people's needs. For example, I would find it scary if my camera mounted in my bedroom, which task is to detect faults, would just process all the data in the cloud. Furthermore, if you want to install a camera-based application in an industrial environment, you have to make sure that no personal information can be reviewed, can be accessed by third parties. In the end, it's always a question of trust. And the more far away you process the data from your camera, then the more challenges you have to face. For example, you have a limited bandwidth and you have an enhanced latency. I think the majority of these problems can be solved if we process locally, if we process embedded, if we process at the edge. And then, for example, we can promise to our users, okay, the camera cares for your safety, but no image will leave the sensor. We call this privacy by design. But of course, for us developers, this means another bunch of new challenges. So we have to change our algorithms so that they can be put into the embedded device. We have to live with limited resources, like limited memory, like limited power consumption. Or for example, we have a limited flexibility, even if requirements change. On the other hand, with this approach, we are able to create highly scalable systems and in turn create trust. With our Hemistereo NX 3D vision camera, we want to encourage developers to create their own omnidirectional image processing applications at the edge. Therefore, the camera is equipped with an integrated edge AI processor ready to process your classification, your detection task. And it is arranged as an open software platform. Developers get full access to all resources that are present within the device. Since we love diversity, we support a wide range of software frameworks and machine vision tools. For example, you are able to create your algorithm in Python or C++, and then you can optimize parts for CUDA and then let it run in real time within the device. You may access your own processed data within the device itself, or you can make a remote access, for example, via gRPC interface. However, it's always your choice. In order to support developers for rapid application development, we provide predefined software infrastructure. For example, our pre-installed Ubuntu Linux distribution comes with several pre-packaged images. So for example, you might install Jupyter Notebook and you can get directly access from your browser software to the device. With the script editor, then you can quickly start realizing applications. Use OpenCV for image manipulation. Then you can use integrate predefined CNNs in order to perform rapidly intelligent scene inference. And then you can, for example, return the result via gRPC to a remote PC. The sample application shown on the right side of the slide has been realized in approximately 20 minutes. That's it. Omnidirectional edge AI. I would like to close this talk with some words about my team. At 3D Vision Labs, we are currently 10 colleagues comprising of engineers, comprising of developers, marketer, and administration. Together, we share the passion for omnidirectional vision, for 3D cameras, and of course, for AI. On the behalf of my team, I wish you an exciting and successful OmniCV. So I would like to thank you for your attention, and I'm now happy to answer your questions.
Let's see if we have any question in the chat. Else I could have one during this time. So what do you think is the hardest part to go to the edge? Is it the connection to the hardware? Is it try to do the programming? Can you give some insight?
You mean the challenges?
Yeah.
Okay. In the very first, I think the challenge is the hardware itself. Because when you want to realize a powerful edge component, then you have to face the challenge to put a lot of computational power into a small package, into a small place. So you have to face a lot of challenges, for example, power consumption, for example, thermal issues. And then, of course, you always have the challenges with the software, because if you want to put large neural networks into small embedded AI devices, then you have to face a limited resource on memory. But then you have to think about how to shrink your networks while still keeping somehow the performance. So I guess it's a mixture of hardware and software.
I could ask one more question. So regarding the device, like what do you think matters the most for the industry? Is it the size of the device? Like the smaller it is, the better is it? Or is it more about accuracy and just latency?
I guess this highly depends on the application you want to realize. For example, I told about different applications. If you want to, for example, monitor the vicinity of an autonomous vehicle, then I guess parameters like accuracy, parameters like latency play the most important role. But for example, if you put the device in the production area, in order to monitor processes, in order, for example, to make a stock level monitoring, then the velocity or the frame rate is not that important. Then you have to provide compact devices. You have to make sure that the images stay within the device, that the workers, for example, accept the device. So these are more crucial parameters for such kind of applications. It's always highly depending on the application you like to realize. That is why, as you surely know, we have a variety of different 3D sensors in the market. This is because almost each and every application has its own requirement set, and therefore makes it sensible to realize own 3D cameras.
Yes, thank you very much for making this point. I think it's very important to notice, like between research and industry, like somehow for research, we focus on enabling an application. But like when we are in industry, somehow we want to target multiple customers and they have specific needs. So somehow we need to divide and create specific targets. So it was a very important point to make. So I want to thank you very much for this talk. It seems that we don't have any question in the chat. Do you want to make any last minute comments, or we can jump to the next speaker?
It was a pleasure for me to be part of this session and of this event. So once again, thank you very much for giving me the chance to present 3D Vision Labs here and to present our contribution to that research area. And maybe we will get one or another feedback from colleagues that see this video. This would be very nice. And so thank you very much and good luck to the next presenter.
Thank you.
Okay, thanks, Michael. That was a really interesting presentation. So just moving on to the next presenter, Jujun Hu, from a professor at MIT's Department of Materials Science and Engineering. He's authored over 100 journal publications, is a recipient of multiple awards, including the SPIE Early Career Achievement Award and the DARPA Young Faculty Award. His research focuses on integrated photonics and meta-surface optics for applications in sensing, imaging, and high-speed comms. And his talk today is on a single-piece omnidirectional flat lens. So thanks a million for coming, and we look forward to your presentation.
Okay, thank you very much, Jonathan, for your kind introduction. Let's see. Okay, maybe could you quit the screen share, because I can actually share the screen here. Okay, great. Oops. Okay. Oh. Hello, can you hear me now?
Yes, we can hear you.
Yes.
Okay, yeah, I apologize for the technical issue. My Zoom just crashed.
No problem.
Okay, so first I want to thank the organizers for their very kind invitation for me to participate in this exciting event and cross-disciplinary exchange. As I mentioned, I'll be discussing about some innovations that we had on developing new omnidirectional flat lens. Now, before I go into more technical details, I want to start by acknowledging the team that actually did the work. So Dr. Mikhail Shalakinov, he is a postdoctoral researcher in my group that actually demonstrated this omnidirectional flat lens. And Fen Yang, a grad student in my group, as well as Dr. Tian Gu, a research scientist I collaborate closely with. They are the ones that actually formulated the design and the theory behind this flat lens. Today, I'll also be discussing about some algorithm development in designing of such a meta-surface device. And for that, we are actually collaborating with Professor Hualang Zhang's group at UMass. And the work is sponsored by DARPA under the Exchange Program, as well as Lockheed Martin Corporation. So here's a little outline of my talk. I will start by introducing the basic physics underlying such a wide field of view fisheye flat lens. And then I'll proceed to discuss about experimental demonstration of the first fisheye flat lens. Then I'll switch gears a little bit and then discuss about some deep learning-based inverse design algorithms, which I believe could actually bridge computational imaging as well as the hardware innovations. And just to show one example of the capabilities of such a design algorithm, I will show how we can actually apply such an algorithm to enable broadband fisheye meta lens design. And before I summarize the presentation. Okay, so to start with, what we are trying to create essentially is a fisheye lens with high performance and yet with a small footprint and hopefully with low manufacturing costs. Now, if you look at conventional refractive optics, while they can actually achieve very large field of view, close or even exceeding 180 degrees, but to minimize any optical aberration, the price you have to pay is that you need to cascade multiple optical elements so that you can minimize any image aberration here. Now, the downside, of course, is that this becomes a more complex and a more expensive optical assembly process. So the technology platform we are looking to resolve this challenge here is to go to a kind of device that's called a meta surface, or sometimes people also call it a sub-wavelength diffractive optics. Now, to understand how meta surface works, we can take a look at this lens here that again relies on conventional refractive optics. So in this case, we have a curved geometric surface, and in effect, this curved surface actually creates a position-dependent optical phase delay, because light have to go through this high-index glass media with a different thickness or depth. Now, this phase delay profile then creates a convergent wavefront that eventually allows light to focus at one spot. Now, if you go to a meta surface, we then create on a flat substrate an array of sub-wavelength antennas, optical antennas, or sometimes we call them meta atoms. By controlling the geometry of these meta atoms, they can actually impart phase delay on demand. So you can then actually construct a phase delay profile that closely resembles the classical case. Now, provided that the dimension of these meta atoms is smaller than the wavelength, then what optical theory shows that then in this case, light will not be able to tell the difference between these two cases here. And what you get is also a focusing lens, like in the classical case. Now, I want to mention that the challenge of expanding field of view has been very well recognized in the meta surface community as well. And there's been some very nice prior work that has looked into cascading multiple meta surfaces to expand the field of view. So the best they have demonstrated is that with the doublets, you can actually reach a field of view of 56 degrees. So now the question is that can we actually build on that and do something even better to realize omnidirectional imaging? Now, this is the architecture we come up with. So what we have here is a flat piece of transparent substrate, so essentially glass. On top of that, in the front surface, we then pattern an optical aperture. And then on the back side of the same substrate, we then pattern this sub-wavelength scale meta surface. Now, when light comes in at different instant angles, they then pass through this aperture, get refracted at the front surface, and then impinge on the backside meta surface at different but continuous portions. By designing the phase profile of the backside meta surface, we can then achieve high quality focusing across the entire 180-degree field of view. Now, one thing I also want to mention here is that the focal plane is actually perfectly planar, so we can easily get this camera to work with a standard flat CCDs or CMOS images. Now, one thing I also want to highlight here is that the idea of incorporating aperture to enhance the field of view in optical systems, again, is not new. If you read this paper back in the 1980s, people have already proposed that by using aperture stop along with a diffractive lens, you can actually expand the field of view of conventional optics. But for a very long period of time before our work, the best field of view that people can accomplish with such a configuration is up to only 30 degrees. So what we want to do here is to explore the limit of such an approach and see if we can actually significantly enhance the performance. So to do that, we need to actually understand what's the physics behind such a wide field of view optics. So to model such a wide field optics, we developed this kind of generic model here, where we have one aperture, we have one meta surface sitting behind, and then here's the image plane. So now we consider two light rays that comes in through aperture and then get focused at the same spot on the image plane here. Now, according to the basic theory of optics, if you want to get a stigmatic or ideal focusing, the light path lengths of these two different rays must be the same when they reach the focus point. So this allows us to actually formulate one equation that relates the phase profile of the lens to the position of the focal spot on the image plane, or this position, this parameter d here. Now, to solve this d so that we can get a closed form solution, we then look at another case here where we now have two sets of light rays coming in a slightly different incident angle, but they pass through the same aperture area on the metal surface. So then they get focused at different spots. Now, if we assume that the phase profile of the metal surface is relatively independent of the incident angle, then both light rays should see the same metal surface, and therefore this allows us to give another equation that then explicitly express the position of the focal spot in analytical expression. So now by combining these two sets of equations together, we actually derive an analytical closed form solution for the optical phase delay profile of the metal surface we need to achieve a wide field. We then go ahead to verify that this analytical expression is actually valid. So for that, we are looking at essentially a Strawman wide field view metal surface system that we are targeting close to 180-degree field of view, and in this case, operating in the mid-IR wavelengths of 5 microns. So we perform brute force numerical optimization to design what is optimal phase profile, and we compare that with our analytical results. And as you can see from this figure here, we can get very nice agreement between the two, showing that indeed this analytical approach allows us to design such a wide field optical system with high quality. Now, if we switch our attention to the bottom figure here, we also simulated the performance of such a lens across the entire field of view close to 180 degrees. And what we are seeing here is that the metal lens can maintain a high focusing efficiency of above 75% across the entire range. And it also maintains a high imaging quality manifested by the high Stewart ratio here. So Stewart ratio is a parameter that's used to gauge the imaging quality of such a lens. Normally, if a Stewart ratio is about 0.8, then people consider this lens to be so-called diffraction limited, or essentially aberration-free. So in our case, we were able to achieve such a diffraction limited, aberration-free imaging across the entire field. Now, one more thing I also want to mention here is that when we derive this analytical expression, the only assumption we made here is that the separation between these two light rays here is actually very, very small. Now, in reality, we want to work with a lens with a finite aperture so that we can have enough optical throughput. So we also actually extend analysis to the case of a finite aperture. And what we are looking at here essentially is optical path length difference for two light rays that go through the center of the aperture as well as through the edge of the aperture. Now, by looking at optical path length difference, we were then able to gauge what is the aberration that's caused by such a finite aperture effect. Now, we are going into the details of mathematical derivation. I just want to highlight that this analytical expression allows us to give a very specific guidelines as to how to optimize imaging quality of such optics. So what we are seeing here is that if we want to have high image quality, we will need to actually constrain the aperture size to typically a few millimeters across. The F number, the sweet spot, is around F2 optics. Okay. And also having a larger substrate thickness also helps with imaging quality. But the trade-off here, of course, is that the system actually gets larger and thicker. So this constraint shows that this solution here is definitely not a universal solution for all applications, but it will also help us to define what are the target applications where our technology can best be adapted to. So now let me switch gears a little bit and talk about experimental demonstration of our technology here. So we started out by essentially doing a prototype that operates actually in the mid-infrared wavelengths of 5.2 microns. But I want to mention that we choose this wavelength just for the convenience of our experiment. This architecture is pretty generic and can be easily adapted to any other wavelength. So we fabricate the metal lens, we perform the measurement. What we're showing here at the bottom here is actually a focal spot profile we measured at different incident angles. And what we are seeing here is that we have good quality focus spot across a field of view of 170 degrees that maintains the square ratio consistently above the diffraction limit. So simply put, we now have a diffraction limited lens that can cover 170 degree field of view. We also go ahead measuring efficiency of the lens. Our theoretical prediction is that the lens should maintain about 60 degree efficiency. Our experimental result is a bit less. We have a focusing efficiency of about 46 to 32% across the field of view. And again, we attribute this to some fabrication errors or inaccuracy during the process that can be further improved. We also perform some imaging demonstrations to show the wide field of view capability of the lens here. What we do is that we actually image the standard USAF resolution targets across the entire field of view. And what we are seeing here is that if you go above the incident angle of about 60 degrees, you start to see a significant distortion here where the horizontal direction is actually getting stretched. I want to emphasize that this is actually inevitable because what we're trying to do is trying to map a hemispherical field of view into a flat imaging plane. So in this process, distortion is actually inevitable. But the key point here is that the resolution of the lens is not getting compromised. We can still clearly distinguish all these horizontal bars that gives us a resolution that's very, very close to aberration-free ideal resolution limit. So besides demonstrating this imaging capability in the lab, of course, we also want to demonstrate imaging capability in outdoor environment. Okay, so what I'm showing you here, this is actually a panoramic image of Paris. Okay, now at this time, of course, it's very, very difficult to send a student abroad to actually take pictures like this. So what we did instead is actually perform a simulation, a virtual experiment, to see what the image is going to look like if we subject such an image to our fisheye meta lens. Now, despite being a simulation, I do want to mention that simulation takes into account all the optical effects in the meta lens, such as diffraction and aberration. So what it comes up, if you look at this image here, again, you see this kind of large barrel distortion that's characteristic of a wide field of view lens. But despite that, you see that the lens actually maintains very good imaging quality across the entire field of view. You can clearly see even the individual pedestrians in this case. Okay, so our work has actually attracted quite a bit of attention here, and it actually also got selected as one of the top 10 MIT research last year. So now with that, I want to actually switch gears a little bit and then discuss about a slightly different topic of how to combine such meta surface design potentially with computational imaging. So this is often characterized by the term of so-called deep optics. And the idea behind that is that we want to be able to co-design both the optics front end, the imaging instrument, as well as image processing algorithm in this case, so that we can optimize the performance of the entire system in such an end-to-end manner to target specific applications. Now, to realize such kind of deep optics that can be optimized both hardware and software fronts, now one important aspect in terms of optical front-end design is capability to realize arbitrary point spread function or PSF engineering. So what I want to show you here is that we have developed an algorithm that allows us to actually engineer the metal surface optics to achieve arbitrary predefined point spread functions. And we believe that this could be a useful tool when combined with the backend processing algorithm to optimize the imaging quality. Okay. So just to show how this algorithm works, we started out by using actually a deep learning-based design to design the large meta-atom library. And then we use optimization algorithm to optimize the layout of such meta-atoms across the entire optical aperture before we validate the design using essentially brute force computational validation. So through a collaboration with our UMass Law collaborators, we have developed a deep learning algorithm that can essentially go both ways. You can start it out with an arbitrary geometry of the metal surface, and then it will predict what the response is going to look like. Or you can start it out from optical response, such as spectral dependent spectrum, and then it goes back to tell you what are the actual designs you need to have for the specific geometries. Then with this kind of algorithm, we then have a large meta-atom library. We then use the so-called direct search algorithm to then optimize an array of these meta-atoms across the optical aperture. The idea behind such a direct search algorithm is pretty straightforward. Essentially, sequentially go through the entire optical aperture and replace each meta atom with the optimal design to maximize the field of merit. We then go through this process multiple times across the entire aperture so that we can actually get the design with optimal performance. So in this case, we can actually engineer specifically the field, the point spread function of the optics. So as one example to illustrate the power of such a design algorithm here, we decided to tackle the problem of wide field operation of meta lenses, which has always been a challenge for meta surface. In this particular example here, we show that designing such a meta surface against the same optimization procedure, but now apply to a conventional multi-level diffractive optics. We see that in all cases of the design optimization process, the meta surface lens always exhibit enhanced performance compared to a multi-level diffractive optics. And that's because we have now this freeform design that can offer much better dispersion compensation compared to just a simple diffractive lens. We also expanded design to a wide field of view and also broadband meta lens. And in this case, this shows the optimization results. We can maintain a very good focus spot profile across the entire field of view and also span a half octave bandwidth. Okay. Now, in terms of specific performance, we show that across the entire field of view, as well as the half octave bandwidth, we can maintain the diffraction limit performance with a compromised focusing efficiency of about 34%. While this seems low compared to conventional optics, I do want to mention that this is actually quite favorable compared to other designs that have been reported in state-of-the-art meta surface optics. So we can also apply such an algorithm to design the point spread function also to other kind of applications. So then just to summarize, with such a technology, we are now actively exploring different kind of applications here across both sensing, imaging, as well as display. Now for display applications, I just want to mention that we can also use a system essentially in a reverse manner. Instead of receiving image, we are actually projecting image over this omnidirectional field of view. Okay, so they could also be useful for wide field view displays. Okay, so we are certainly more than happy to actually explore any potential collaborations you may be interested in any of these application areas. And like I said, we believe that the algorithm, inverse design algorithm, will be actually very, very useful when it's actually combined with new computational imaging algorithms here to actually enable application-specific optimization for the entire system of both hardware as well as algorithms. So with that, I want to conclude my talk, and I'll be happy to take questions. Thank you.
Thanks a million, Joo-Jun. That's a really interesting topic. Maybe I'll start with a question, and I think it's actually very relevant to the next speaker as well, for building cameras. With the manufacturing process for these single flat lenses as opposed to your standard multi-level diffractive optics, what is the difference and the complexity involved in developing them?
Okay, great question. So for fabricating the meta surface optics, the patterning step is usually done by essentially standard microfabrication. So what we are doing now is that we are exploring using a semiconductor foundry deep UV lithographic process to actually fabricate the meta surface structures. So this is a process that's kind of very, very similar to how people use to fabricate essentially electronic chips. Okay, so it's a scalable manufacturing process. In terms of conventional optics, this is of course done by using essentially mostly plastic molding for low-cost optics. The only challenge here about manufacturing of meta surface is actually the volume. Right? If you are only trying to manufacture a few thousands of them, then the cost becomes very large because to set up the mask and then to fabricate them is quite expensive. But if we're talking about hundreds of thousands of units, then the cost essentially scales down very rapidly because the setup cost is the same. The actual manufacturing cost of each unit is actually quite negligible in this case. So with some cost modeling, what we found is that when the volume goes above about a few hundred thousands, then the manufacturing cost of the optics will be on par with conventional molded plastic optics. The additional benefit for meta surface optics, of course, is that we also need only one optic element. So we eliminate any kind of alignment assembly process that could also cut some costs there.
Okay, and I guess a similar question. I mean, like the actual the optical resolution of the lens. Then does that scale, or is this, how does that work?
Okay, so the resolution would depend on essentially the f number, right? The aperture size. So there's indeed some trade-offs here. So if we want to, like I showed in one of the previous slides, so lens works best for relatively small aperture, as well as the limited f number, limited to about f2 optics. So we believe that this technology probably is also best operate for like kind of mini cameras and kind of small miniaturized camera. This is also where their kind of size and weight benefit is most fully leveraged.
Okay. Okay. I'm trying to see, is there any other questions coming from your? I could continue with another couple maybe. I guess
I can ask one if you.
Yeah.
About the materials. It's like for the lens, like can we consider like there is multiple options to do a lens, like glass, plastic, and can you speak about what is the best? Like, do you have recommendation for young researchers that want to work on optics?
Sure. So if you're specifically talking about metal surface optics, the material combination is really pretty generic. Anything that's optically transparent and with some index difference with respect to air, you can make metal surface out of it, right? Now, if you consider practical manufacturing constraints, our favorite material choice in this case is actually some kind of glass substrate, because that's compatible with semiconductor manufacturing, and also essentially CMOS compatible materials like silicon nitride, silicon, as well as silicon carbide. Those are the material choice we are exploring for kind of practical applications.
Thank you for all the details.
Maybe another one for me. I guess what is the downside? There must be some downside.
Okay, yes. So there are already some limitations here, right? Like I said, if you are trying to scale the aperture size, you want to large optics, that's quite challenging. If you want very high numerical aperture or large f number, that's difficult. And also, if I try to apply this to a broadband applications, there's some trade-offs as well. You always have to either sacrifice the aperture size, sacrifice efficiency, or sacrifice imaging quality. Okay, so that's why we believe that probably the best application for such optics is for something that requires relatively narrowband operation. Okay, like work with LEDs, active illumination, for example, or you work with few discrete wavelengths, like in the case of display, right? And also something that ideally small and compact. Okay, so that's kind of the typical applications where we're targeting.
Okay. So have you looked at thermal cameras or anything like that, or does it matter the wavelength you're looking at?
The wavelength is pretty generic. We can go with essentially any wavelength as long as it's kind of narrowband. So for example, like medical imaging, this is one good application. We use active illumination. 3D sensing too, because you essentially also use active illumination. So those are kind of key applications we're looking at.
Okay. Any other questions?
I have a question, if you don't mind. So I was wondering, like in kind of traditional fisheye optics and things like that, there's optical aberrations that we're sort of used to. You've chromatic aberrations, you've varying optical resolutions and things like that. And either we fix them, optically, or we just kind of put up with it. We know it exists. We put up with it. We work around it. You seem to kind of fix quite a few of these issues with this metal lens design. But what I guess I'm wondering is, and maybe it's kind of related to Jonathan's question just now, is there any kind of those aberrations that we should look out for if we started using your lens design, your metal lens design for computer vision or something like that?
Great question. Yeah, I think ultimately the best solution is always to combine both the hardware and the software, right? Because for example, like if you're looking at this barrel distortion, there's really nothing we can do about it from the hardware end. And as long as you know kind of how the point spread function varies across field of view, you can correctly use using software. Okay. And also some of the limitations I mentioned, like limited f number, right? Limited wide spectrum operation. There are already people trying to look at how can we use some backend processing algorithm to correct for those if you know the response, optical response of the lens system there. So yeah, this is something I'm definitely very interested in, exciting direction. I would be happy to look into any collaboration opportunities here.
Okay, thank you.
Yeah, maybe just one more question for me. Sorry, just in terms of the intrinsic calibration of a camera, have you looked at this in terms of how how isotropic it is from a center of projection? Have you looked at how smooth it is, I guess, in terms of an intrinsic calibration for a meta lens?
You mean essentially kind of across a few of you in different directions?
Exactly. Yeah. Yeah.
Okay. Yeah. So we did that, and in fact, in this experiment here, we specifically choose a direction that give us the worst performance. So this kind of bottom line performance.
Okay.
Yeah.
Okay. Okay. Thanks a million, Jujon. I think this is a really interesting topic, and thanks a million for presenting it. If there's no more questions, we'll move on to the next speaker. Thanks a million.
Okay, thank you very much.
Okay, so the next speaker is Enda Ward from Value Vision Systems. He's he leads the camera architecture group in Valeo, defining the next generation automotive vision products. For those who don't know, Valeo supply omnidirectional cameras globally to multiple car manufacturers, enabling driver assistance and automated driving systems. He's worked in automotive for 15 years, and he holds several patents in the field of automotive vision, and he's also a Valeo master expert. So thanks to Enda for coming to talk today. He's talking on automotive vision systems, opportunities and challenges for the future. So take it away, Enda.
Thank you, Jonathan. Thanks for the introduction. I'll just share my screen now. I think you may need to stop sharing, Jonathan, actually.
Sorry, I think it's Mark, is it?
Yeah. Should. Can you see it now?
Yes, go ahead.
Okay, perfect. Thanks very much, and thanks for inviting me to speak today. Very honored. So yeah, looking forward to go through an overview of automotive vision systems. As Jonathan mentioned, I've worked in this space for 15 years now. Started back in 2006 in the early days of camera sensing in the automotive world, and it's changed a lot over the last few years. So just to give you a high level, I won't spend too long on the company intro stuff, but just to give you a high level overview, Valeo are a global tier 1 in the automotive space, spread across a lot of different areas in the industry, not just driving assistance systems, visibility systems, cleaning, widespread product portfolio there in the different business groups. My area is within the comfort and driving assistance group, and particularly in the area of camera systems, which we developed. So we're based in Tuam in the west of Ireland. We manufacture and design I suppose the full ecosystem which makes up the modern automotive vision system. So from the camera side of things, we develop the camera, the ECU processing, then the embedded platforms with the image processing for both computer vision and visualization purposes, and also we develop the end user functions. So I guess one of the key advantages from our perspective that gives us is because we're involved in all parts of the chain, that we fully understand the challenges both of the manufacturing side of things in terms of the real world challenges and constraints of it, to feed into our end user applications and what we can and can't do from a computer vision or a visualization perspective, and to provide a more holistic solution, which I think is key in any domain. So just to give you a quick background on the growth of automotive over the last few years. Historically, we would have been viewing systems only. Funnily enough, the first product vision system which we developed almost 20 years ago was actually a wireless camera, not Wi-Fi, but wireless. Since then, it's grown dramatically into rear view cameras, surround view cameras. As things evolved then, there was a growth into the inclusion of analytics. So analytics processing to add onto the visualization became more and more dominant within the industry, I guess, particularly with the advent of CNN, ImageNet competition really pushed, I think, every industry in that direction. But there's been a huge acceleration, I would say, in the last 5 to 10 years in machine vision, computer vision in this space. As that's moved on, we also have more fusion of sensors. So fusion of camera sensors, of camera algorithms, but also with LiDAR, with radar. And then off vehicle has been a key enabler. And really what we're seeing this trend is the edge was mentioned earlier in one of the other keynote talks, where the edge is the vehicle, the edge is the sensor, but also the cloud connectivity, the culmination of this sort of swarm intelligence where you have multiple vehicles cooperating with the infrastructure. And that's really the trend we expect to see more and more over the next 10 years. In terms of a high-level architecture, what things look like, you will have multiple cameras within the vehicle, depending on the particular vehicle type, cost point, feature sets provided, etc. By and large, from a vision perspective, we have wide-angle fisheye cameras, which will be the core focus for today in the context of this workshop. We also have far-field vision, which are I dub narrow field of view, but can be up to 120-degree fields of view. So it really depends on your context of what narrow is, I guess. And then in-cabin sensing, which can actually go from fairly narrow field of views from 30-40 degrees up to actually fisheye applications as well. So with the context of wide angle and fisheye, we see use cases both exterior and interior to the vehicle for multiple applications. In terms of using that data then, so yes, we do computer vision, but with the end goal of driver assistance functions, automated driving enablement. The vehicle display then is another way to inform the driver with first for driver assistance, but in the future, as I'll explain, with comfort type features. And in the future, we also see more off-vehicle feature functionality. So where we consume that data, really where the automotive and consumer worlds start to merge together. And we start consuming that information in lots of different ways, you know, on our mobile devices, on our smart TVs. Really what I, again, expect to see over the next 10 years is a real blending and merging of these technologies. So here I'll focus on a couple of the key areas. As I said, front sensing is your 120-degree, 100 to 120-degree wide field of view camera for high-speed driving, in-cap type applications, safety functions. Key area of focus today is on the 360 cameras for around the vehicle. So typically you will have 190, 195-degree cameras. Using traditional optics yet, we're not at meta lens technology, but certainly something that looks interesting and promising for the future. And then for in-cabin applications as well, we see the use cases. Again, a wide range of field of views there. Just to talk through a little quick overview on some of the use cases. So high-speed driving, typically, as I said, that's a narrower field of view, longer distance ranging. But as I mentioned, fusion of the cameras of the vision from a computer vision perspective is becoming more and more important, both in terms of redundancy in some cases as a fail-safe mechanism, but also in the case that you want to get a different perspective, that you can't see part of the road with one camera, for example. So really that the various cameras on the vehicle can complement each other. High-speed driving presents a lot of challenges in that speed is one of the challenges where high speed, the risks are higher if something goes wrong. Low speed and urban driving presents a different challenge. So the speeds aren't as high, but for sure in an urban environment, you know, 50, 60 kilometers an hour can cause damage and seriously injure or kill somebody. So safety is certainly a concern. But one of the real challenges once we get down to lower speed maneuvering in cities and in urban and suburban environments is that it's a less controlled environment. There's more things can happen. On a freeway, typically, yes, it's high speed, but you're in lanes, it's constrained. It's a very much more constrained environment. For sure, there's events that can happen from time to time. However, an urban and a suburban is much more haphazard in terms of random events, the long tail events which can happen. And I guess for us, that's one of the advantages of wide-angle fisheye, having that 360 perception cocoon around the vehicle, that it gives you that wide overview of all those cases to keep an eye on things that may happen, monitor and predict eventualities. So for example, automatic emergency braking forms a key focus to support in that. Other use cases are 360-degree HMI for parking applications. And again, as I said, to enable that 360 cocoon, current vehicles, it's often used, you know, that are on today as a driver assistance, as a visualization back to the driver. But more and more already on premium vehicles, we're using that for parking systems for a number of years, where the vehicle is in control, where we have analytics taking that data, making decisions to help and assist the driver at the end of the day. And then we move to sort of home parking environments. Again, it's a constrained environment, but one of the key challenges we have in this is that a road has got lots of fixed regulations. Lane markings are this size. Traffic signs should be a certain regulation. There's more control on it. Once you go to a home parking environment, you know, there's lots of different garage scenarios, objects left around small children running around. So it's a different set of challenges. Lower speed, but more challenges to work with. So we see the use of SLAM as a key enabler in these spaces to map the scenario around the home on a personalized level, and that's a key topic I think we'll see more and more of for the future, as you get a more personalized experience as we move into future applications. Another key change I guess we'll see over the next few years is a real revolution in mobility. So currently we have privately owned vehicles are dominant. We're all aware of the push in the market by new mobility players who are pushing new technology solutions, pushing for level 4 automation. And for sure that will continue on. But we also see a lot more of that technology coming in to the privately owned vehicles. So there'll be a mix of that in the future. And on top of that, I think the pandemic in particular has one thing that's come out of it is lots more online shopping, lots more distribution. The concept of having delivery automated has become more and more a key part of our future society. So the use of droids, of smaller delivery functions, of automated trucking services will also be a key part of the future technology. And all of these, again, benefit from computer vision and visualization as enabled for these technologies. So what's the transportation future look like from an architectural perspective? Historically, to date, everything has been on vehicle. The topic of edge is always an interesting topic for me because it really depends on your perspective as where the edge is. For me, the very edge is the sensor itself, the camera module. You can have the processing unit on the vehicle as an edge, the vehicle itself as an edge, and then infrastructure as an edge. So there's multiple phases of edge computing that will continue to emerge at different phases over the next few years. But also we will see more cloud and this balance between cloud and vehicle infrastructure start to grow in importance over the years, and the exchange of the data between them. So defining common interfaces will be key. Agreement on how that data exchange goes, and also ensuring that data is exchanged in a clear and safe path. As I mentioned also, the automotive and consumer worlds will continue to merge together. A couple of example use cases we see and we've demonstrated within Vallejo over the last number of years is use of augmented reality. In principle has been around for a long time. A rear view camera has graphics on it. But more futuristic views of that would be translation, for example, of a wide-angle camera from one vehicle to another, for example, as we've demonstrated in our extra view demos, where using the camera stream from the vehicle in front of you, you can get a visualization to see, is it safe to pull out? Is it safe to overtake? And really providing new perspectives around the world as you connect the streams together. With that comes challenges. The rollout of 4G connectivity, 5G connectivity, what data rates are possible, what processing do we on vehicle, what do we do off vehicle. Another use case which we see in the future is using if we've enabled an automated world, which we continue to do over the coming worlds, how can we now make use of that? What are the consumer level functions which can be enabled by that? So virtual reality is one use case we have examined, and also, you know, streaming to smartphones and TVs in addition. So I'll give you an example of our Voyage XR. Hopefully this will stream okay.
The audio isn't coming through in the.
Okay, that's fine.
I think you have to change how you share your screen.
That's fine. I can talk through it in any case. I suppose the key message really here is we're streaming 360-degree cameras from the vehicle. We have the concept here now that you have a grandmother who's sitting at home, her family are driving, for example, through California on a road trip, and they want to share the experience with her, show them what they're doing, make her feel immersed as part of it. So we have the use case of virtual reality, whether it's a virtual reality headset, whether it's a tablet or a smart TV. We feel really that that's going to enable you know, key features and use cases in the future. So really using that video data, not just for, you know, the standard ADAS functions, which are key and critical, but also for sharing experiences and enabling new consumer content. Okay. Okay. So that's the easy bit. That's the concepts. Now, how do we make it a reality? So there's a few challenges to get there. Continuing on all the time, these continuous challenges which we work with and develop solutions for. I guess the key first one really is reliability in automotive world, right? So automotive, we ship it from the factory. It needs to work for the lifetime of the vehicle. That might be 10, 15 years and beyond. And in fact, those timelines are increasing as we move to electrification. You know, reliability in vehicles and drivetrains increase. You know, the reliability use cases become more and more. We use the vehicles more and more. I mean, traditionally, you have a privately owned vehicle. It sits in the driveway. You know, you might use it, in fact, 5 to 10% of its whole lifetime because it sits in a parking lot. But as you go to new mobility use cases, the use of the sensors and the processing technology in the vehicle will increase. So it introduces more challenges in terms of how do you handle that data. A key thing to consider, I guess, from a computer vision perspective and how we work with that is, I guess, we like to work in an idealistic world to assume we've got a camera input, it works all the time. The reality is not that. You know, we have complex lens assemblies, camera assemblies, optics made of mechanical components, you know, plastics, glass, which vary and will adjust over time. And also we have very tight tolerances in terms of the application needs that we might need to meet in terms of the MTF performance of the camera module, for example. So bearing that in mind, you can't guarantee that you will have the same performance for the entirety of the lifetime. You can't guarantee you'll have the same performance over the temperature range. So it's a key consideration both from a design point of view, both in a camera module, but also in computer vision to understand what the challenges and the limitations are and trying to find the best balance. And that's the type of technologies we work on a daily basis to push forward the best overall solutions. Other challenges we face in the automotive industry are, again, daytime conditions are good, nice to drive around on a sunny day, but if the sun is too bright, if it's shining into the vehicle, if you have nighttime conditions with very poor lighting, if you have adverse weather. So again, lots of solutions in play to work with those advances in image sensor technology, you know, the optimization of F numbers to get more light into the sensor. But then you're balancing that with the trade-off. We have smaller pixels, which are pushing the challenges continuously. We want smaller pixels because we want higher resolution. With smaller pixels, we decrease the low light. So it's this constant balance. And at the end of the day, it's cost. For sure, we have high-end applications where you say these are big vehicles. We spend lots of money on them. The reality is this technology is trickling down to the mass market, and mass market ultimately is consumer driven. So it will be always cost at the top end, as a key dictator in terms of technology and driving what's possible and what's not. So continuously working between these forces of the technical engineering challenges with meeting the cost, and then ultimately what the end application need is. And I guess as an industry, that's something we're all still working through. You know, the new use cases are developing, understanding the capabilities of the machine learning platforms as they develop, what they can deal with, what they can't. And there's some exciting developments in that for sure in terms of what can be compensated for and what can't. Okay, technical challenges are one side. One other challenge from a non-technical perspective, in fact, and I know we'll have a discussion on Woodscape later on, but in terms of us releasing Woodscape as a data set, as you probably realize, took almost a year, I think, in delay of getting it out there. And the reason for that was actually a number of non-technical challenges, but more from topics such as privacy, data ownership, where it's stored, things like that are key. So we need to consider what are the functions being used for, how is the data set being managed, how are we storing it, ensuring compliance to the laws in particular regions, which vary from country to country. So awareness of that is a key thing that needs to be considered. Will the data be just consumed for display purposes in the vehicle? Will it be transmitted off vehicle? Will it be just consumed by an algorithm? Or will it be displayed to somebody at a later date? So again, lots of considerations in terms of that. And in fact, as part of the Woodscape dataset that was released, anonymization was a key part of it. I know we worked with Brighter.ia as part of that to enable that, and it's a key consideration in future as we work to both drive the industry forward in terms of technology, but we need to be respectful of the norms and regulations that are there for very good reasons, to be fair. On the other side of it, then, this is where this constant, I guess, battle comes in: privacy versus safety. So yes, we want safety. We need autonomous driving features to have driver safety, improve, societal performance in the future. But with that becomes, okay, well, how do we manage that data? How do we work with it? Also, there's the safety of the big brothers. There's obviously been lots of topics over the last number of years about, law enforcement getting access to doorbell camera recordings, things like that. So these will be topics that will face, I think, all industries over the coming years, and really need to come up with overall solutions. It's not necessarily just for automotive, it's consumer board across the board. And wide-angle cameras, I guess, pose a particular topic to consider there, because of their nature, we have a 360 view, we have lots of viewing of the environment. So we need to be sure to work together as an industry in tackling those challenges. And ultimately, ubiquitous computing is to enable these new feature sets that we want to drive the industry forward and drive society forward, so that there is a seamless interaction between our consumer and our automotive world. So it's trying to find the best balance between the non-technical and technical challenges on that. So I'll finish up on now on sort of some of the future trends. Really, sensing, image sensors are continues to increase in resolution from sort of 2 megapixel up to 8 megapixel and beyond. Typically, these are lower than what you would see in obviously in consumer applications, but really because we're driven by low light performance being key for automotive to ensure we get the best performance in the maximum amount of use cases and environmental conditions we can. The connectivity, the data rates will increase for sure with that, which brings its own challenges in managing that data. Processing of that data. So it's a key question for sure. Do we want more pixels, or do we want more TOPS to process those pixels? And this is a continuous topic of discussion in the industry, and ultimately comes back to cost, to form factor. There's lots of trade-offs there. With that data then becomes more and more, we will grow more and more from terabytes to petabytes to exabytes and continuing on. So managing that data, as I said, in a safe manner will be a key path into the future. And ultimately, how we connect that data on vehicle or off vehicle, so 4G to 5G connectivity, will form a key part of the future in transmission of that. So look, in summary, as we said, the automotive world is continuing to transform. We move from standard privately owned vehicles to new mobility opportunities of the future, exciting new use cases, which we need to work on. With that becomes definitely robustness, reliability will be a key. these are critical to ensure that we all enjoy a safer future. And it's not just the technical side. There's technical and non-technical challenges which we are working on and as an industry to overcome. So yeah, that's a high-level overview of it from my side. Hope you enjoyed the talk. Thank you.
Thanks a million, Enda. Very interesting talk. I guess we're open to questions now. I see for everyone that's on YouTube Live, I mentioned it on the chat. Again, if you have questions for the speakers, please put them into the chat, and we can for sure ask them. So there is a question coming in from Manuel Ray. So are inputs from cameras enough condition for engage, disengage, or it always needs to be backed up by other sensors for final decision? I guess this is in reference to
fusion of applications, I guess.
Carpathi's talk at CVPR as well. Yeah.
Okay, for sure. Look, I think from our perspective, from a Vallejo perspective, really, we do see a combination of functions in the future. There is no one sensor node that can solve every problem, and for sure we do envisage, certainly there's some use cases where you will have just one sensor input and you will rely on that, but we see a combination of sensor inputs into the future. So both vision systems, and it's also important to consider from a redundancy perspective, it may not be just vision and radar. We might have a surround view system and an automated driving camera, okay, which are effectively different sensors. So we can have redundancy across computer vision aspect side of things, but for sure we envisage the use of LiDAR, the use of radar, and other sensor modalities as part of the overall decision making, for sure. It's context dependent and a complex topic, but yeah, we envisage multiple sensors into the future.
Okay, thank you. Question from Pierre: How is Vallejo thinking about privacy? I like seeing faces sharing video streams between vehicles, hacking, spying, or even passive attacks like taping cameras or breaking lenses to block vehicles.
For sure, it's a key area of it for us. So cybersecurity is a key topic we take very seriously within it. Continue to work on it, I guess, from an application perspective, from a overall system solution, working with the OEMs on the overall end system solution. So for sure, it's a challenge I think faces not just Vallejo, the overall industry, and it's really something that needs to be taken seriously and is something we work closely on. So from cybersecurity, from our design point of view, and also from a production perspective, I suppose it's a full encompassing, and also you bring in other aspects of it. There's a functional safety side of things. There's the SOTF side of things as well. So there's a number of different avenues where we look at to protect those scenarios.
Okay, thanks, Enda. Any other questions from the live chat?
I can ask one more. So if you think about young researchers that want to work in the automotive industry, like there is so many companies out there. So do you have a recommendation about how they could make their choice to try to work there?
Oh, of how to get there.
Yeah.
For sure. Yeah, I mean, look, it's an exciting space at the moment. I think a key topic is, I mean, there's always good opportunities from a student level. Is for example, Vallejo, we offer student and internship opportunities. So there's always options there to get involved. I think the other thing is there's actually a lot of good courses online as well. Just that can be done for free, even in advance as part of your studies, if it's not directly part of your course, if you're in an undergrad course. So I think there's multiple education opportunities, there's internship opportunities. We also have various, even visiting the websites, getting a lot of the information to understand the technology. There's a lot of information out there. And look, if you're interested in Vallejo, I'd say feel free to reach out. We're continuously hiring as well. We hire not just experienced engineers, we hire graduate engineers as well. So very open to anyone who's interested in any of the areas. As I said, from my perspective, we cover mechanics, optics, production, hardware designers, computer vision expertise, so right across the whole chain. So yeah, feel free to reach out if anyone's of interest.
Great. On that note, is there any other questions? Oh, sorry, Pierre. One 360 camera versus multiple small large field of view camera. So yeah, one single, yeah. One
Sure. Yeah. No.
omnidirectional.
Yeah. There's a couple of concepts on that. So there's a couple of different people have come out with solutions. So one approach is you take one 360 degree and you just record the scene and build up a picture, for example. Some of the trade-offs in that is you don't have necessarily a live view. So that's one challenge with that, particularly when you're getting into more safety-related application sets, where time and latency is critical. So that's one thing just to take care on, I guess. The other aspect then is you might have, for example, one camera on the top of the vehicle trying to see omnidirectionally. In an automotive application, it's extremely difficult to capture all the use cases with that. And particularly when you consider 360, you're concerned, if you see a big SUV, you want to see the rear of the vehicle, the front of the vehicle. A camera on the top of the vehicle just won't have the visualization to see that. So there will be a lot of blind spots extended around the vehicle. So at the moment, for where we're getting to, to improve, tighter parking solutions, to improve safety around the vehicle, we see 4 as the optimum. We started off actually, we had 5 cameras in the days before 360, so we're down to 4, but we think 4 gives the optimum performance to enable the next generation feature sets.
Great. On that question, I think we might wrap it up. Pierre, I think it's for a 15-minute break now, and then returning with Giovanni in approximately 13-14 minutes time. 15-minute break. Okay.
Yeah. Thank you very much.
Thanks.
Perfect.
Yeah, I'm gonna.
Thank you, guys.
Thank you.
Okay.
Thank you.
So, hi all. Hope you all had a decent coffee break. We'll continue now with the next speakers. I know I've found the speakers this morning so far anyways really interesting, and I'm sure that Giovanni's and Zach's talks coming up will be just as engaging. So I'd welcome Giovanni Pintori to speak now. Giovanni is a senior research scientist and engineer at the CRS4 Center in Italy. In his career, he has coordinated and managed several international research and industrial projects in various fields, from space exploration to security management in urban environments. His research spans many areas of computer vision and computer graphics, including panoramic scene understanding, multi-resolution representations of large and complex 3D models, and 3D multi-view reconstruction, as well as kind of new generation mobile graphics. So Gianni will talk about fast and automatic 3D reconstruction of indoor environments from omnidirectional imagery now. I'll just stop the sharing if I can. Do that, stop sharing now. That should free it up now for you, Gianni, to share.
I see. Okay. Is this okay?
Yeah.
Okay, fine. And then hi everyone. Thank you for that kind introduction. As we mentioned, I'm working on the topic of this workshop since several years, even if my background along 20 years at CRS4 come from computer graphics. CRS4 is a research center mainly focused on computational sciences applied to different domains like bioinformatics, physical modeling, simulation, visual and data-intensive computing. The center is located in Sardinia Island and was founded 30 years ago, attracting research and scientists from many places in the world. CRS4, or Visual Computing Group, leads research activities in different areas of computer graphics, computer visions. Our primary focus is the study of scalable technology for acquiring, creating, and even exploring massive and complex models, and the integration of this technology in real-time interactive systems. The application of our technologies are in different real-world domains. For example, environment simulation, cultural heritage, security. Over time, the applicative interests have shifted from big models, for example, of planetary scale, in support of space and Earth exploration, to the interactive exploration of detailed terrains. For example, at the time of Google Earth, you made some works. And also arriving to the urban domain, which has become strategic in light of increasing urbanization and its problems. So in this context of urban environment, an important scenario for research and its applications is the indoor environment. This is quite obvious. We spend most of our time indoors, so we have also experienced it in particular in the last 2 years of pandemic. A lot of indoor stay. So while for outdoor scenes, standards acquisition and reconstruction pipelines reached a high degree of maturity, in the indoor environment, there are still open research problems. In this context, the main targeted output is usually the structured indoor model. This is not just the detailed reproduction of the visible scene, but a structured representation of it. We can think about this model as an abstraction of captured data into main elements and their relationship. So this representation can be, for example, a graph where the nodes are functional part of the scene, like rooms, walls, floor, ceiling, objects, and the edges are the geometric relationship between them. So this graph has a topological part, that is the obvious connection graph, and the geometric part, the shape of the various components, and even a visual part. So we deal with the appearance model of the different nodes. This representation serves two fundamental goals, usually in the reconstruction. First, simplifies the semantic analysis of the scene and enable a number of domain-specific applications. For instance, indoor navigation. Second, constrain the output, so simplify the reconstruction. The structure indoor model can be reconstructed from different inputs. The most easy to acquire and common source is the visual input, like images, but also we can capture geometric data, for example, by laser scanning, or having a mixed input, visual and geometric, like RGBD capture, for example. A typical acquisition setup usually provides high resolution color data and, on the other hand, has very sparse geometric coverage. This is typical of depth sensor, which have more density on the horizon and for the near objects, for example, and also by multi-view stereo pipelines. So it's also typical for indoor scenes acquisition, which are very featured by multiple occlusion, textureless surfaces, and even more problems. Should be noted that the visual input is also important, if not always necessary. We have, in fact, purely visual pipelines, but also we can use visual data for scene understanding and the semantic segmentation of the geometric data acquisition, which is required for a structural reconstruction at the end. Both for the visual or mixed mode capturing, the capturing is usually performed in two different ways. General, we have hand-held scanning, most like video, for example, or in-place acquisition, which is commonly acquired with a full view panoramic acquisition. Hand-held scanning is assumed to be denser than in-place capture, but requires continuous motion planning, as we know, and even high computation. So it is usually adopted for a particular task or small indoor scenes, or SLAM task, for example. Static acquisition is instead becoming a common solution for the capture. Even professionally, you can think to the Matterport 3D acquisition, for example, and cover large and small environments with the visual sensor, but also using geometric measuring station. It provides the capturing of large and complex scenes with just few shots. And even if geometry is more sparse than handheld video, the different scans are more stable and easier to be registered. In the indoor context, a common trade-off for capturing is to exploit a single shot or a less single image for each room. This is a reasonable solution, since a single spherical image contains a lot of information, and this information can be efficiently analyzed in a unique context. Also, capturing a single panoramic image is an easy task even for a common user without the need for a specific or professional skill. This is very important. We speak about privacy in the previous talks. In the indoor case, differently from public outdoor spaces, it's not obvious that the scene can be accessed by outsiders, even if it is a professional acquisition. So such single view solution can be used both for common, usually common users, but also for professional solution. Single view solution furthermore can be extended to larger and multi-room scenes by exploiting 3D registration between different poses. In this context, two common research problems are first, the recovering of the indoor 3D layout, and second, the estimation pixel-wise information, such, for example, the depth. And recovering the 3D layout consists in the reconstructing the geometry of the bounding permanent surfaces underlying the scene. Should be noted that it is common in this context, especially in computer vision context, to define as 3D layout only the bounding surfaces, even if the 3D layout, we know that is a more general concept, which actually should involve objects and also other functional parts of the scene. Another important problem is the pixel-wise estimation of other information, where the most common task is the depth estimation, but also the semantic normal estimation and more. About the first problem, recovering a layout from a single image is usually challenging. we know that we have many occlusions from furniture, objects, even by the structure itself. To this end, it's necessary to complete many missing parts by adopting solution on a restrictive space. For example, the indoor world model, where we assume that we have a single horizontal floor, a single ceiling, and a right angle for the wall. So this model is commonly implemented in the fundamental concept of geometric context and Manhattan vanishing lines. So such concepts are also adopted during pre-processing in many depth learning pipelines for omnidirectional images, where the pre-processing is followed by the prediction itself and followed by a post-processing Manhattan world regularization. And another crucial problem is with the spherical images is the distortion. Such distortion usually affects the recovering of regular structure, such as in the indoor layouts, for example. A typical approach is to use the image transforming. So that important feature preserved in the transformed space. An example of this approach, here we have a paper tangent image with mark, where the equirectangular map is efficiently converted into several undistorted representations. Such approaches are useful to improve performances of the feature structure and also to improve the performances of CNN networks. Here we present an example of a solution that tries to address both the problem of two restrictive priors and the spherical distortion. The solution is called AtlantaNet, and as the name suggests, it employs the less restrictive Atlanta world model, in which the environment is restricted only to the horizontal floor and ceiling and vertical walls, but without limitation on the wall shapes. So, supporting, for example, non-right angles, curved walls. In this approach, the equirectangular image is encoded as a two horizontal projection. So encoding the room layout as an undistorted 2D footprint on the floor plan and a single height value. So the network architecture is based on convolutional layers applied to the projection themselves. And then we have an RNN module to deal with the occlusions and the occluded parts. The network takes as input ceiling and floor projection, as in the scheme here, of the original equirectangular image encoded by our ResNet. To capture both the low level and high level feature, we keep the last four feature maps of the encoder, and then we encode for each pixel a fixed side feature vector, so that the 2D feature map is flattened in a one-dimensional latent feature. That is, at the end, we obtain a sequence of feature. We feed such sequence to a RNN network, and then we have only to upsample the output to recover the probability map describing the ceiling of the floor shape. It should be noted that in this case, the indoor priors we mentioned in the slides before are embedded into the data encoding itself, assuming, of course, the Atlanta projection. Here we show some results on common benchmark like Matterport, Stanford, and also on specific scenes not limited by the indoor world constraint. Here in the dataset, Atlanta layout that contain scenes with complex wall layouts or curved walls, footprints. And then the second problem, another important task in the indoor reconstruction is the dense and pixel-wise information prediction. So the most popular problem of this kind is the depth estimation. And not only, we know also that we have semantic normal information that can be recovered with very similar, if not the same, pipeline. The typical problem to face is the spherical distortion here. As for the layout, many recent work used to convert the spherical projection to a set of perspective images. The goal here is different. It's not to recover structure, since we are not oriented to a particular structure, but to obtain undistorted images to feed the standard pinhole pipeline. To descend different strategies that have been exploited, for example, we have distortion-aware convolutional kernels, cube map projection. We also have recent orthogonal works that try to exploit the correlation between the depth, the room layout, semantics, to improve the wall prediction. Such approaches require more information, of course, to work, and usually they work in a restricted production space. Recent alternative solution, like Pano pop-ups, for example, is focused on mostly planar structure, where the indoor prior is imposed directly to in the loss function, giving maximum loss to the sample that lie on planar surfaces, for example. Here we present a recent alternative solution called SliceNet, presented at this CVPR. And then the solution directly works on the equirectangular domain without the need for planar transform or distortion-aware filtering. This work proposes a compact representation of the image features, exploiting the properties of an indoor environment. Starting from the assumption that gravity plays an important role in the design of man-made environments. This approach proposes a representation of the sphere map as a set of vertical slices in form of a sequence of relative features. For the encoding part, we introduce a slice-based representation as a set of slices of the sphere, resulting in a set of fixed site features covering the wall equirectangular image. The slicing is obtained by compressing the feature map along the vertical direction and preserving the horizontal resolution. So we obtain for each slice a gravity-aligned feature vector, and for the whole scene, a sequence of fixed site gravity-aligned feature. For decoding, we have a sequence of representative latent gravity features, one for each slice of the viewing sphere. Having a sequence enables us to use RNN scheme also here to find long and short-term relationship between parts of the scene and to refine the feature. The final decoding is very simple at this point. So just performing an upsample of only on the vertical direction. It should be noted that the indoor prior, in this case, it is the dominant gravity direction, is embedded in the network structure itself, not in the data encoding or in the loss function. Here we have some results using public dataset and benchmark. In particular, our method seems to provide consistent performances for real-world dataset, for example, with Matterport and Stanford dataset. From the qualitative point of view, our method finds a more accurate depth even in areas with smaller and repetitive structural details. Here we can see first row, the bottom right figure, or in the case of large environments, the second row, the bottom right figure, and also for non-Manhattan world but regular environments, as in the case of the arched vaults. And you can see in the last bottom right figure. To summarize our discussion, modern single panoramic methods provide in some way impressive results. They give many advantages for ordinary user in terms of easiness of use, speed of acquisition, reconstruction. So methods can be also used for important cross-domain applications. We have the need for a specific or professional skill. This is very important. So they are very user-friendly, but the overall quality is good and results are obtained at interactive rates. But on the other hand, such results are not enough for professional users. From the layout side, for example, typical problems are given by big occlusions or by the oversimplification of the output model. We have just sparse corners, and in a similar way, depth estimation suffers from missing samples and also from a problem of spatial coherence between different poses, real world measure and scale. And for the future, Several promising solutions, in my opinion, are given by data fusion approaches, for example, boosted by modern RGBD panoramic sensor, as we have seen previous talk too, and also we expect to combine the results obtained from a single panorama by integrating multiple omnidirectional poses, even without deal with an expensive dense acquisition. Both these two goals can be obtained looking for solutions directly in the 3D space. This is very important because, as we have seen, that all the previous solutions are restricted to 2D or 2.5D solution space in a simplified way. That's all for my talk. Thank you for your attention. If you have questions, I'm here.
Great, thanks, Giovanni. So open to questions. I have one. Maybe more kind of general kind of question for you is that in terms of, let's say, how about what in terms of use of spherical cameras for computer vision? What if somebody was starting out new to that field, new to using spherical cameras and looking to do some projects with it? What would be the kind of gotchas with spherical cameras compared to maybe kind of standard cameras people might have kind of focused on in the past? Maybe that's a tough question to answer.
First, we have we have new and modern devices here now. So all the reconstruction, if you think, for example, to single omnidirectional image reconstruction, it was almost impossible since a couple of years ago, since we have, for example, to stitch only to obtain one single image, we have to obtain it just stitching manually the image. Now, in other words, we have sensor, as you have seen, that are able to acquire in just one shot one omnidirectional image, one shot, and then we can acquire video, and then we can easily combine more than one image. Okay. To combine images is also easy because if you are working in a controlled space, for example, using tripods, using cars with other instruments, so in other using sensor fusion, it's very easy to combine the information between omnidirectional images. Also easier than try to combine the information from pinhole and perspective image. This is a big breakthrough respect to the previous years. So because omnidirectional image, also in my experience, are not for steady acquisition, but they are also important robot exploration, because it's very easy to follow a path using omnidirectional camera. So it's very easy to connect the different images between them. On the other hand, also is depth sensor with the visual part, and so all this integration can do more in the future.
Super, thanks for the answer. There's a couple of questions coming along on YouTube. So Pierre's asking how to combine layouts to a consistent one, like a floor plan.
Oh yeah, good question. In the same way I've mentioned, since, for example, a work like Atlanta network layout, usually they return a probability map for that room. It's very easy to, once the images are registered between them in a multi-view setup, okay? Yeah, it's very easy to add this probability map in order to cover more than one room. Of course, you need that the images, the different poses are related in some way, okay? And the easiest thing is to obtain a couple of images where we have a common feature. Once the images are registered in a common word, in a common reference frame, it's possible to add the solution. An important thing, if you look to the solution of, I go back to the layout part, for example, here. Okay, just here. Okay, here we mentioned that in our work, for example, at AtlantaNet, we don't perform any regularization. That is, the solution is not a Manhattan word regularization like happened in other work, for example, but this is just the probability map of the shape. Okay, so in this way, it's easy to add this probability map in the same reference frame of another camera, for example. And also, I also just to say that is an open problem. It's still, if you look to the papers, it is still an open problem to make something or layout for larger scenes without using very restrictive prior. AtlantaNet use the Atlanta priors, but in an ideal work, we expect to have 3D reconstruction without such restrictive prior, of course.
Yeah, makes a lot of sense. So Samuel Bruno on YouTube is asking, on AtlantaNet, you use traditional convolutions on the image. Have you tried to use spherical convolutions instead? They appeared some years ago, and I think you referenced, in fact, Mark Eder's work, which is in kind of in that space.
Actually, I didn't try other kind of convolution. Of course, this is a standard solution that use a residual network. So in order to be compliant even to the encoder, and also in order to make AtlantaNet easier to integrate with other systems. Okay, for example, if I want to integrate AtlantaNet with SliceNet or depth or semantic extraction, it's very easy since we have a common encoder, a common baseline. However, I know, since we also made experiment that there are even better way to filter the data, also to make other kind of convolutions. But this is different, since other kind of the filters are probably more suitable for depth reconstruction, pixel-wise reconstruction. That is different because in this context of the layout, as I define the layout, is the underlying scene, is not the scene as we are seeing in the depth. The depth instead see everything, see clutter, see furniture, so we can use the typical convolutions. We are using the convolution on using all the data we are seeing. Here the problem is almost opposite, since we have to filter between permanent structure and clutter.
Sure, makes a lot of sense, yeah. Sorry, I know we've gone over the time, but actually our next speaker hasn't shown up. So I have a couple more questions still to ask you, Gianni, where we have the time, if you don't mind.
Okay, they can contact me by email or whatever you want.
Well, we have time now because our next speaker hasn't shown up, unfortunately.
Okay,
yet. So Pierre was asking another question. He said, houses are furnished. Does clutter, such as furniture, impact the guest layout, either positively or negatively?
Oh, sorry, I didn't hear the question.
So Pierre is asking, houses are furnished. Does clutter, that is furniture, impact the guest layout, either positively or negatively? So how does clutter?
Okay, yes. Okay, yes. In this case, it's a negative. So clutter, furniture here is treated as a noise, as a as a something that is not ideal. Okay, in the ideal world, we don't have clutter, we don't have furniture, so AtlantaNet doesn't reconstruct the clutter. So consider this is like just occlusion. And the clutter, and even modeling the clutter in this case doesn't help. Although in my previous work, and I used the clutter and so modeling the bounding volume of the clutter and the furniture in order to improve the reconstruction of the layout itself, okay, and of the underlying structure. And the point is that it's not easy to find data of annotated data. I mean, there are some interesting and important scientific data sets even containing furniture, annotated furniture, but we don't have real world except the last one work that is presented in this workshop, I guess, where we have annotated furniture and objects. This is very important since in my experience, real world data works better than scientific data. Okay, especially for challenge tasks like recovering a very occluded structure and so on.
Okay, that makes a lot of sense. I guess a question as well is, where do you see kind of indoor understanding going in the future? Like, is it layout to 3D scene graph with objects, or how do you see the research developing in future, basically?
So first step, I think that the first step is to remove all the priors we have. Think that we have to use less priors. So I expect to have just vertical or semi-planar or piecewise planar at least, but is not enough since we have many modern structures that are not for sure covered by this model. Especially, you know, AtlantaNet, but also we have a lot of real good work that are still working on the indoor world model. So this is not acceptable. So I think that using data fusion, so using even geometric measure mixed to the visual information can help to go beyond the use of such priors. And then the second, the other step, of course, as the previous question asked, is to work with a larger and work with many images, so work with more complex structure. This is the future, but this is strictly connected with, since we are speaking about depth learning and data-driven solution, is also connected to the availability of data sets. I think also that even produce a good data set, real world data set can be very useful for the future.
Absolutely. Yeah, no, thank you, Giovanni, for that, and thanks for taking questions beyond the timeline. It's
thank you.
Fascinating talk, and yeah, really fascinating talk. So one of our speakers hasn't shown up. So what I suggest we do is take another break for 15 minutes so that we keep the kind of schedule going properly, and that we just basically take another coffee break for the next 15 minutes. And then we'll come back with the first of our oral speakers for our papers. Thank you again, Giovanni. I really appreciate the talk. It was really good.
Thank you to God for all your efforts. And okay.
Great. Thank you. Do you mind stopping sharing the screen if you don't mind? Thanks. Hello and welcome back. I'm pleased to say that we will have our first oral paper presentation now. So Elad Plout is going to talk about 3D object detection from a single fisheye image without a single fisheye training image. So I'll just unshare my screen and it'll free up Elad to share his screen. Over to you, Elad. Yeah.
Okay, so hopefully you can see my screen. So yeah, I'm Elad Plout, and this is joint work with Erez Ben Yaakov and Batel Shlomo. We are from General Motors. Hold on. Okay, so before we talk about 3D object detection in fisheye images, let's recall how monocular 3D object detection works in perspective images. So here the magnification is inversely proportional to the depth z. So the object can move to the right and to the left and thus change the Euclidean distance from the camera. But as long as z is constant, then the size in the image is the same. So the ratio between the 2D size in the image and the 3D size in 3D space is the focal length divided by z. And this provides convolutional neural networks an important cue for depth estimation. So the neural network predicts the 3D size and rotation of the object and the 2D location in pixel coordinates, which provides the ray pointing towards the object. And the depth z can be directly regressed because the convolution operation is translation invariant and the magnification is also translation invariant. And this gives the 3D bounding box. But fisheye images are very different. There is no shift invariant magnification in fisheye images. When objects move to the right and to the left and up and down in the image, then their size, shape, and appearance change in the image. Now, we all know that you cannot just undistort and warp the fisheye image to a perspective image because it's impossible for a perspective image to capture a field of view of over 180 degrees. And even if the field of view is smaller than 180 but large, then the warped image is still impractical. But fisheye images can be warped to cylindrical images. And there is an interesting relationship between straight lines and curved lines in perspective images and cylindrical images. So here on the top left, you see a picture of a wall, a famous wall in Jerusalem. And on the bottom, you see the cylindrical image. And in the cylindrical image, it doesn't look straight anymore. The wall looks round. And on the top right here, you see a picture of the inside of the Colosseum in Rome, which is round. But in the cylindrical image, it looks straight. Now, the objects, the people, they are clearly visible. And we can even imagine how when they are smaller, they are more distant. So is there a shift invariant magnification in cylindrical images? In perspective images, we project objects onto a plane. In cylindrical images, we project objects onto a cylinder. So we use cylindrical coordinates where a rho is the cylindrical radial distance and phi is the azimuth angle. And there is an intrinsic matrix that multiplies the cylindrical coordinates to give pixel coordinates. Now, in perspective images, we said that the magnification is inversely proportional to z, and this doesn't apply to cylindrical images. But if the object is not too large and not too close to the camera, then we can use a first order approximation and say that its width, which is a straight line, is approximately the length of an arc. And under this approximation, we noticed that we get a shift invariant magnification that is inversely proportional to rho, the cylindrical radial distance, instead of z. And what we discovered is that if you take a monocular 3D object detection that was designed for perspective images and was trained only on perspective images, and you show it a cylindrical image, then it processes the image as if it were a perspective image, and it outputs predictions that would create the image if it were a perspective image. And all we have to do is apply a transformation to the output as a post-processing step to move the predictions from this imaginary pose, from this optical illusion, to the real pose. And here are the transformations to the position. So what we're doing is we're taking the fisheye image, we're warping it to a cylindrical image. Then we show it to an existing monocular 3D object detection that was trained only on perspective images. We used the well-known monodisc detector that was trained on the new scenes dataset. And we make two modifications to the output. The first is trivial. The ray pointing toward the object is found using the inverse intrinsic matrix and cylindrical coordinates rather than Cartesian coordinates. The second modification is non-trivial. The distance output, z, must be interpreted as rho, the cylindrical radial distance, because the z distance, the forward distance to the imaginary object that the detector predicts, is actually rho, the cylindrical radial distance to the real object. And also you have to change the angle, because now the horizontal pixel coordinates are proportional not to the tangent of the angle, but to the angle itself. So you really need our non-trivial insight about interpreting z as rho to get the correct bounding boxes. So here on the top left, you see what happens when you just try to apply the monodisc detector, which assumes the perspective projection, to a fisheye image, which obeys the fisheye projection. And obviously the 3D bounding boxes are wrong. And on the top right, you see what happens when you use our method and you project the 3D bounding boxes back to the fisheye image. On the bottom left, you see the predictions projected onto the cylindrical image, which is what the neural network actually sees. And on the bottom left, you see what happens when you take into account the cylindrical coordinates only in the ray pointing towards the object, but you neglect to use our insight about interpreting z as rho. Here are a few more examples of detections. This is a test set of real fisheye images that we collected in the United States. The only public data set that was relevant was a data set of simulated panoramas from a paper by Grégoire Payan de la Garanderie et al. They also proposed a detector for these panoramas, so we compared our method to their detector on their data set, and we performed significantly better. Even the recently released Woodscape dataset has not yet released 3D bounding box annotations, but the lack of data only emphasizes the high value of our method, which does not require any fisheye training data. I will say that the main failure case of this method is before I said that this works if the object is not too large and not too close to the camera. But when it is large and is close to the camera, such as this example, you can see that its front wheels appear as though they're pointing away from the camera, but the back wheels appear like they're pointing slightly towards the camera. So the object is banana shaped. It doesn't look like, if it were a perspective projection, it wouldn't be a cube, it would be a banana shaped object. So you can imagine that if this were a bus or a truck, it would be even more severe. And a detector that was trained only on perspective images would not predict accurately, at least not the orientation of this object. So I will end with a video of detections on the real data, the fisheye images that we collected. This is without any temporal smoothing or tracking. And I think we have time for one or two questions.
Great, thanks, Elad. Maybe one question from my side, or maybe more of a statement. It's really that with the perspective projection, your translation invariance happens when you translate the object at a constant distance from the camera, whereas with the cylindrical, I guess it's kind of a rotation of the object leads to a translation in the image. That's kind of basic, and that's why you're saying that it works. Is that you have some form of kind of translation invariance, albeit it's caused by rotation about the camera or about the cylindrical view rather than translation with constant depth. Yes, the right interpretation.
Yes, it doesn't matter where the object is in the image. It could be in the right side of the image, in the left side of the image, at the top of the image, at the bottom. It looks the same in the cylindrical image as long as its cylindrical radial distance from the camera is the same. Much like in the perspective image, it doesn't matter if the object is on the right side of the image or on the left side of the image, as long as its depth z is constant.
Yes, whereas with let's say raw fisheye, there's no kind of translation invariance readily available.
Exactly.
Okay, that's brilliant. Thanks, Eli. That's a great presentation and a great paper. I've read it already.
Thank you.
So what we'll do is we'll move on straight away to Georgios's presentation. So yeah, welcome my second oral presentation from Georgios Albanis, who will speak on Pano 3D, which is a holistic benchmark and a solid baseline for 360-degree depth estimation, which is a really important topic as well. Over to you, Georgios.
Thank you for the introduction. Are you able to see the screen and the slides?
Yeah, we can see it.
Thank you. So I'm Georgios Albanis from Visual Computing Lab, and I'm going to present you Pano 3D, a holistic benchmark and a solid baseline for 360 depth estimation. So monocular depth estimation is the task of inferring a per pixel depth map from a single RGB image, which can be used to deduce scene geometry, which information can be applied in several downstream applications, including 3D reconstruction, virtual tours, or floor plan generation. However, monocular depth estimation is a challenging ill-posed problem, meaning that several 3D scenes can correspond to the same 2D image. On the other hand, the availability of data has enabled progress in the data-driven methods, achieving great results in the domain. To that end, several studies focused on complex loss functions for improving performance, while others focus on refining the initial depth predictions in order to improve the estimates. More recent works have been focusing on mixed datasets for essentially testing the generalization performance of the different methods. Following that progress, most works in the omnidirectional domain focus on either adapting the convolutions or the architecture to the spherical domain, while others adopt a joint optimization approach for boosting performance. Even though these approaches have achieved great results in the domain that have moved the state of the art further, they still neglect most of the advances in traditional depth estimation domain. To that end, we introduced Pano 3D, a benchmark that offers the data, the methodologies, and the solid baseline in order to assess the depth performance estimation across different architectures, loss functions, and datasets. Overcoming the challenging piecewise smooth nature of depth maps, Pano 3D consolidates the evaluation methodologies of various works to assess direct spherical depth performance estimation, but as well the model's performance regarding boundary and smoothness preservation. Additionally, we offer a 3D performance metric, which is useful for several downstream applications, including view synthesis and mesh reconstruction. But also going beyond that, we also assess the generalization performance by following a zero-shot cross dataset transfer approach and evaluating the generalization ability of each model, considering different data distributions, camera color transfer function shifts, and application to scenes with different contexts. But in order to achieve this, we first need to introduce a large-scale dataset, which leverage existing 3D scan datasets like Matterport 3D and Gibson, and essentially resulting in a total of 662 scenes with a high diversity across all the previous aforementioned axes. Particularly, we provide splits that varies in terms of distribution, like Gibson medium split and tiny. Additionally, splits that include non-residential scenes, but preserving the same depth distribution as the original dataset. Additionally, we provide splits with high variance in the camera color domain for Gibson Tiny and Gibson Full Plus. Therefore, we believe that the proposed dataset allows for testing the generalization ability of the models across the 3 different axes, approximating real-world scenarios very well. Finally, even though we have not included this split in the submitted paper, we provide another Gibson split, namely Gibson Full, in order to further support research in the 360 domain. Having introduced the data, now we are able to thoroughly investigate different architectures and loss combinations in order to eventually provide a solid baseline. But as we said before, our analysis is going beyond direct depth performance estimation evaluation and includes as well depth, boundary, and smoothness preservation metrics. And to facilitate the selection process of architecture and loss function, we resort to a set of indicators that essentially aggregate an error and an accuracy metric for each trait to facilitate the selection process, as I said before. As our analysis goes beyond, we conclude that actually skip connections assist performance as the best performing architecture was a unit. But also you can see here that a modified ResNet architecture with skip connections significantly performs better from its counterpart. It seems that the addition of skip connections allows models to capture fine-grained details, as you can see here. I mean, to capture the object boundaries and edges and so on. Apart from that, we show that the global loss function, like virtual normal loss, it's more useful to architecture that have a limited receptive field, like unit architecture, and not to other ones. Such losses allow capturing contextual cues like edges and object boundaries, as you can see in this image. Apart from that, another important observation is that it's difficult to find the best trade-off between the smoothness and between the different metrics. For example, you can see here that the PNAS architecture was the best performing model in the smoothing metrics, but not in the boundary ones. To that end, we introduce a periodic refinement architecture, which takes into account the horizontal discontinuity of the rectangular projection. And we show that this refinement step actually improves the performance in the boundary metrics for all architectures except unit. We also observe that the performance degrades when tested in splits other than Matterport, as you can see here. But it's worth highlighting that the most significant drop occurs in the scenes with the contextual difference, like the Gibson Full Plus. And then the second significant drop is in the filmic splits, which have the color domain, the camera color domain variance. To that end, we introduce a CP photometric augmentation technique, which actually boosts the performance in the filmic splits. And this is actually expected, as we said, this is the splits with the most intense difference in the color when compared to the trained dataset. Finally, we also highlight that the architectural adaptation should be considered when working in higher image resolutions, as the reduced receptive fields does not allow models to capture object boundaries and preserve the object structure. We also observed that this issue was not handled even by complex loss functions like the virtual normal loss, which worked very well for the low resolution. Finally, we compare the delivered baseline with an indicative state-of-the-art model like Bifuse to in the wild data captured either by a 360 camera or by a smartphone. It can be shown that the proposed baseline yields better results, even when the input is not a perfect panorama, having artifacts from the stitching procedure. For more qualitative results, you can always visit our project page, and thank you for your attention.
Brilliant, thanks, Georgios, and just on time there. I don't see any questions coming through, so what we'll do is we'll go straight to the lunch break then.
Okay.
So we'll have our lunch now. We'll return at about 12:30 Central Time, about 45 minutes from now. Then Saravana Balaji will present on the Woodscape Challenge and announce the winners. And I think the winners of the challenge will also be giving a talk, I believe. So that's all after the lunch. Okay, so please enjoy the break and see you soon. And thank you very much, Georgios, for the good presentation.
Thank you, Kisaran.
Yeah, hello. Can you see the screen?
Yeah, everything is good. You can go ahead.
All right. Hello all. This is Saravana Balaji Ramachandran. So I'm going to be talking about OmniCV 2021 semantic segmentation challenge on the Woodscape dataset consisting of fisheye autonomous driving images. So I'm Saravana Balaji over here, and this is Ganesh right next to me, and then John and Senthil on the right. So John and I are affiliated to Maynooth University and Lero, and Ganesh and Senthil to Vallejo Vision Systems. So before I go into the challenge itself, I'll probably I'll brief on the motivation of the challenge and why we have the challenge in the first place. Fisheye, why fisheye? Yeah, probably you've been hearing it all day for now. For those who missed, so here's the fisheye cameras give a very wide field of view than the narrow vision cameras, the ones that we usually use. So this will allow seeing a lot of things around the car with a single camera. So we've been seeing these ultra wide cameras in a lot of places, actually in phones. Large, a lot of recent phones have ultra wide cameras, and a lot of cars start to actually put them there as well to get a large field of view. So with just 4 cameras, we'll be able to see everything around the vehicle. We can get a complete 360 perception with just 4 cameras. So essentially what this means is we'll be able to get a third-person view of the car from inside the car. So it's like playing a racing game where you can actually see the car while you're driving. So I know what you're thinking. So we can actually replace the joysticks, steering with joysticks, and then yeah, I'm waiting for that too. It's going to happen in years, in a few years, or maybe even months. So essentially, this will allow us to see, let's say, the edges of the cars and all around the car in a greater detail. Very useful for parking and other things. So we have a lot of data sets, autonomous driving data sets. New College, St. Lucia, Kitty, and a lot more in this area, and even the bigger ones that got recently released, like Apollo-scapes, Cityscapes, and BDD 100K, with a lot of images there. But we don't have these are all narrow view images, cameras that capture narrow view images. So there's this need for a fisheye data set, so we can actually improve the vehicle autonomy by giving this 360 perception. It is actually a lot of manual effort and labor in order to get, for example, semantic segmentation labels for fisheye datasets freshly, but there is this necessity to do this so that we can build models encouraging that. So that's where the Woodscape fits in. So it has this 4 fisheye cameras that I showed you before. It has about 9 tasks, which I'll show in a minute. So basically what we are trying to do here is we are encouraging the community to build models that operate directly on fisheye images, rather than using the existing pipeline that take narrow view images that convert them to after rectification and then use them. So the Woodscape dataset has these tasks like object detection, 2D, 3D, motion estimation, depth estimation, and so on. One interesting thing is this lens soiling, where you have to detect the raindrops or mud on the lens. And for this, challenge, we are going to focus on this semantic segmentation part. So another interesting aspect of this data set is that there's this anonymization. So in order to comply with privacy rules and data protection rules, usually a blurring, we can blur out all the human faces in order to being able to personally identify them, and the number plates as well. Here, with the help of BrightRay, what happens is they use a GAN to generate faces, fake faces, and slap them on to the existing ones. So the whole point of doing this is, let's say you have a pedestrian detector, it may not work if you blur the faces. And it may actually work without the blurred, with the actual ones. So with the real faces, it might work well with the blurred ones. So this kind of skews the evaluations, the metrics that we use for evaluation. So this technique is to preserve the deep anonymization, is to preserve this. So the challenge itself was hosted on CodaLab. And it was open to participants from April 23rd till June 16 for about 55 days. So the objective is to produce semantic segmentation masks for RGB fisheye images. So we encourage, basically, we want the community to build novel ideas for fisheye images. And we release the calibration and the ground truth labels for the data set. And the calibration data for the test set was released later, though. So this is essentially the task that we would want to do. The RGB image is there on the top row, fisheye, and we need to build models that generate this output. You'll see quite a lot of colors here. So basically, I'll explain that now. So we have about 10 different labels there, so each corresponding to a different color. So we have road, lane marks, pedestrians, riders, and so on. We also have this wide label. So anything that doesn't fit in these 9 labels go inside wide. And in fact, actually, we have more than 40 classes for instant segmentation tasks. However, we're not including all these 40 because we picked the most important 10 that we think are useful for autonomous driving purposes. And we aggregate them together, or we eliminate them based on whether they are important or not. So we release the so the data set contains the labels for the training set, which consists of over 80% of the data. It contains over 8K images, and the test set has 1.7K images for which the data was withheld for evaluation purposes. So in order to evaluate these models that people submit, there's this trade-off between precision and recall that we need to understand. So basically, systems with high recall, if you're talking about, let's say, road signs, what happens is these traffic signs, the systems with high recall will pick all the traffic signs, and in doing so, they may also pick up some non-traffic signs, so which leads to lower precision. And on the other hand, we have this high precision systems, which will guarantee, which will give some road signs which are guaranteed to be road signs. It won't pick up anything that it thinks is not a road sign. But the problem is, it might, in doing that, it might actually not pick up some actual road signs. So basically, we want high precision for some tasks and high recall for some tasks. So depending on the task, we need to adjust this using a threshold. So basically, we need to tune our system to match what we are doing. So for semantic segmentation, the standard evaluation metric is intersection over union. And how this compares to this precision and recall thing that I talked about is after intersection over union is taken for each category, for each class, for each of the 10 classes, we can then later pick up individual objects within that class and then get a threshold for the IOU for each of the objects, and then classify them as positives or negatives. From there, we can calculate the precision and recall. But here, we are talking about the mean intersection over union for all the classes. So basically, systems with good mean IOU can then be refined to match what we are doing for the particular task. So while taking the mean for all the classes, we don't actually include the wide class. So the reason is we want to prioritize the other classes rather than giving more priority to wide class equally to the other ones. Okay, so we had about 71 participants and a little less than 400 submissions for the duration of the competition. So we which is for 55 days. So we also limited the total submissions to 100 with a and a daily submission limit of 10 applies. So yeah, there are terrible bots out there. we got to protect ourselves from those bots. Yeah, nobody talks about like ghosts, ghouls, and goblins these days. Like they are pretty much harmless, it seems. So yeah, back to talking about human beings. We submitted the baseline. We uploaded the baseline using the PSP net. It's a very good semantic segmentation network for which was originally trained on narrow view images. So with the ResNet 50 backbone, it was fine-tuned on Utscape dataset for about 24 epochs, and this gets a baseline of about 0.56, which is the score. So you can get some understanding of how these systems actually work across these narrow view and wide view images. So basically, I'm telling this to emphasize the fact that making models work on fisheye systems actually requires a lot of customization effort, specifically to work on fisheye images because of the skews and the other things that they produce because of the nature of them. So here we produce. So here I present the top 20 teams, top 20 submissions actually, not teams. The team names are actually given here. So the baseline stands right here at 16. So let me actually focus on the toppers of the competition. A big congratulations to Team Mayton, who's at the first place for winning the competition and with a lead score of 0.84. So the second user is also from the same team. So they agreed to do a joint presentation. Here we are considering them as the same team. So the first team is Mayton, and the second team is BUPT PRIV with a score of about with a score of 0.83, and the third team is Win AI Research with a score of 0.81. So we're going to have a presentation from the first team, a joint presentation there from the first and second user. And presentation, unfortunately, the second team, they're not present today to do the presentation of their technique. And the third one, Win AI Research, so we'll have a presentation from them as well. So here are the ranks that you're seeing here. These are sorted using the score. So the mean IOU includes the mean IOU and mean accuracies are shown here, and the corresponding ranks according for that particular metric is shown in brackets. So the class-wise scores for the individual teams, as of Team 1 and Team 2 and Team 3 here. So you can see that the different techniques, the technique, depending on the techniques that they use, they might score a little bit higher. Maybe if they are the second team or the third team, they may score a little higher for a particular class and maybe lower for other classes and things like that. For example, this one, even though they have a higher score. So this is averaged across all the classes there, except for class 0, which is wide. And I like to remind the fact that this is actually done over 1.7K images there, 1,766 images to be exact. So I'll show you some predictions as well. So here's this column shows the ground truth for this particular. These are 3 random images that I picked, and these are the corresponding predictions submitted by these teams. The first team is here, the second team is here, third team is here. You would actually see there's this trade-off between precision and recall, and you'd be able to observe the same here, some being picked up, some not being picked up. So we'll have the presentation by the winning teams, that the top three teams. Actually, the second one won't be presenting. The first and the third team explaining the method that they use to get the predictions and how they managed to top the leaderboard. So the first team is Meitun, and the team members Jian Qiu, Hai Chao Shi, Xingqiu Shi, Bakong Liu, Xiu Zhang. Excuse me if I pronounce them wrong. So affiliated to Autonomous Delivery of Meitun and Institute of Information Engineering, Chinese Academy of Sciences. So they used SWIN transformer encoder decoder networks to get the top score here with a 0.84 score. So let's welcome Jian Qiu to the dais to present their method.
Oh, thanks for the chair. Can you hear me?
Yeah, we hear you. You can go ahead and take the screen share.
Okay, I'll share my slides. Okay. Hello everyone, I'm a participant on behalf of the team Meituan. Firstly, thanks the OmniCV 2022 Challenge Team Committee for the great efforts to the challenge. It's a great honor for us to participate in the challenge and share the first strong technical solution. Our team members come from Meituan and the Institute of Information Engineering, Chinese Academy of Sciences. Next, we will introduce our method from the following aspects. To the beginning, the pipeline of our method is as follows. Our method is based on the swing transformer. As we know, the swing transformer is recently popular in many research areas using the shifted windows and bears hierarchical feature maps by merging the image patches in deeper layers. Thus, we design two models and adopt ensemble strategy on channel results to obtain the final segmentation results. The first model, as shown on the bottom, model 1, is swing encoder decoder, which is based on the pure swing transformer and use a different operation with the original ones. The second model, we construct the second model, model 2, using the encoder of swing transformer and the deploy V3 as decoder. After the two models are obtained, we then use the voting strategy to fuse the two models' results and obtain the final segmentation results. The detailed architecture of the first model is as follows. Given a batch of fisheye images, a parsing operation is first operated, then MLP layer, known as the multi-layer perception layer, is used for extracting the embeddings, followed by 4 encoders and 4 decoders of swing. It is noted that we design a new swing decoder consists of 3 parts, MLP, pixel shuffle, and the original swing decoder, as shown in the red dotted box in the figure. In detail, the pixel shuffle operation is that we obtain the high resolution feature maps through the periodic shuffling. The second model, model 2, is extracted is illustrated as follows. Similarly, the patching and MLP operations are first operated, followed by 4 swing encoders and decoders. Differently, we extract the ASPP, known as actual spatial pyramid pooling features, in the last layer of the swing encoder. As is known, ASPP is a layer in DeepLab V3, and the ASPP uses the multiple sampling rates to explore the information in convolutional layers and capture the objects and the image context at multiple scales. Thus, we introduced the 2 models that we used. Next, we will introduce the training details. In the training stage, we use the focal loss to train the 2 models and the low-loss loss to fine-tune the model. As we know, the focal loss focuses on training on a sparse set of the hard examples and prevents the vast number of easy negatives from overwhelming the model during training. The low-loss extension is very useful. That can be used for model minimization. And as we know, the low-loss extension of the model of the object function is always convex, and it can be minimized efficiently. The minimum of the low-loss extension can be used to find the minimum of the object function. And both the 2 models use the mix-up EMA cross-validation and multi-scale training strategies. It is noted that we classify the datasets into 9 categories except the void class, and we found that the void class need to be ignored with the observation that there is no punishment that when the void class is predicted into other classes. However, when other classes are predicted into void class, the punishment is essential. The training dataset contains 8,234 images, which is split into 5 folds for cross-validation. In the testing stage, we first use the TTA, known as the test time augment operation, to augment the features. Then we use the voting strategy to further ensemble the 2 models. The testing dataset contains 1,766 images. Next, we will show more visualization results. The left are the original images, and we colored each channel and show the colored segmentation results. We can clearly see the landmarks in the. For example, we can clearly see the landmarks in the 2 images, and the vehicles, pedestrians, and others are also segmented well. Finally, we give the conclusions on our method. We construct 2 models based on swing transformer. The first model is based on the pure swing transformer, and the second model uses the encoder of swing transformer and the DeepLab V3 as decoder. We train our model, use the mix-up EMA cross-validation, multi-scale training, and electric. And in the testing stage, we first use the TTA, and then we use the voting strategy to ensemble the 2 models. Oh, that's all. Thank you.
So if you do any of you have questions, so I'm just checking the chat to see if you have any questions on the chat. All right, so I have a question. So how long did it take for you to actually get the ensembles separately trained? And for example, the multi-scale training, it would take a large amount of time if you had to use a single GPU. If it's not too much to ask, like, can you actually tell us what's the kind of hardware setup that you had to use in order to actually get these things? Is that simultaneous or is that individual?
Oh, okay, thanks. Actually, we used V100 GPUs. Eight GPUs named V100, V100, and we trained the model about 2 days.
Yeah, that's great. So the V100, 32 gigabytes ones, is that right?
Sorry,
Yeah, so I got it. So it's V100s, 8 V100s there for training. Yeah, thanks.
Thanks.
Okay, so following first team, so we have the second team, the BUPT PRAV. Fortunately, they were not able to present today. They used a SWIN network for encoder and HRNet as decoder in order to get the 0.83 score for the second team. So they're planning to actually release an article on arXiv describing the method on how they actually achieve these results. It'll be it'll be released after the workshop in the coming weeks. So congratulations to all the team members there on the second team: Lu Yang, Qing Song, Donggang Yang, Tanfai Zhao, Wengguan Wang, Liu Lei Li, affiliated to BUPT, ETH Zurich, and BID. So in the third place, we have WinAI Research. So they used the multi-head network for multi-view fisheye image segmentation. So they modified the Deep Lab V3 Plus with a multi-head architecture in order to get the scores, and they used an ensemble at the end. They also use a weighted loss function. They'll explain that. So let's welcome An Wo Tran Hai to explain the method.
So can you hear me now?
Yep.
All right. So I'll share my screen, right?
Yep, sure. Go ahead.
All right. Can you see my screen yet?
Yep. All good.
All right. Okay, everything is good. Okay, so thanks for the introduction. Hello, everyone. My name is Anh Vo, and I'll be on behalf of my team from WinAI Research to present our work on the Woodscape Challenge this year. So our method name, multi-head network for multi-view fisheye image segmentation. So as you might know, the Woodscape Challenge this year is about fisheye image segmentation, and there are 9 classes that we have to assign for each pixel. And there are about 8,000 images for training and 2,000 images for testing. And note that the void class is not being used during the evaluation. So we start off with our baseline model, and we train a standard GLab v3 with ResNet ADSB encoder to quickly grab some idea about the data set. So we find that so our baseline model got about 49 mean intersection over union. So as you can, if you take a closer look, you'll see that some classes got very low score. For example, motorcycle got less than 3. So we do some statistic and found that the data set is highly imbalanced, even with just 9 classes. So not only that, we have 4 different cameras, and each camera has its own perspective view, and this adds up to the complexity of the network. So in order to get a high score, we really need to solve these two problems, in our opinion. So in order to solve the multi-view camera problem, right, our baseline model was not very good in that. So to the other end, you might have different network for different camera views, and there's no feature sharing, and the networks are independent. But the downside of this approach is that it will have much less data for training the model, and thus we're not going to get an optimal performance. And this approach is quite expensive in our opinion. And so as you might imagine, that our network is somewhere in the middle. Specifically, we employ a GitLab architecture, and then we extend it with multi-head. Our network have a single shared encoder, and the network split off later to different heads for different camera view. So we hypothesized that with this network design, our encoder can learn better feature representation, since all the data is utilized for training the encoder. And with multi-head for multi-view, each head will have a easier time to learn the unique perspective of each camera. So here we represent how the data flow into our network. Just like we have a shared encoder, and each images is flow to its own path. So we have an experiment with this architecture, and with this architecture, we improve our baseline model about 12 point, and then we also found that the void class, when training with the void class, it actually hurts the model performance. So we just simply ignore that, and we got about 7 point. And next, another problem that we have mentioned earlier in the earlier slide, which is the highly unbalanced data set. So to solve this problem, we propose this equation to calculate a set of loss for a set of weight for the balance loss. So intuitively, the class weight should be the inverse function of its frequency. So here we represent how changing the beta parameter affects the weight. So when beta is small, let's say when beta is 1, the equation is the exact inverse proportion of its class frequency. And when beta increase, we get the class weight evenly distributed. So in our work, beta equals 4 works best for us. And then we apply this weighted softmax loss, and make our experiment, and we gain about 5.84 score. So note that we only use ResNet 80 to this moment, and then we apply more techniques such as multi-scale testing, or TTA, multi-scale testing, and boundary relaxation, which is a technique introduced by a paper from NVIDIA. And we also try to improve the capacity of the network by using bigger encoder. Then we later learned that the front and the rear camera actually share very similar perspective, and the same apply for left and right camera. And so we decided to merge them. And then finally, we do ensemble. So we did not do so much on ensembling, and then we just utilize our ResNet 80, and then with our newly trained ResNet 101. So here we demonstrate how each individual components contributes to our final score. So with border relaxation, it boosts up just a little bit. And with multi-scale testing, we got 2 more points. And with ResNet 101, we gain 2 more points. And with merge head, it improves 0.5 and ensemble also 0.5. So our final score is 80.6. We actually tried some other techniques, but it didn't work for us. For an example, training on distorted perspective cityscape images or attachment images, or use physical CNNs on a structured grid. We also try to apply multi-scale attention, but unfortunately, we didn't make it work. So from this challenge, we learned that with only planar 2D convolutions and some proper additions, we can achieve high performance on the segmentation of fisheye images. And in fact, we are ranked number 2 in M accuracy and number 3 in MIOU. And note that our methods did not use any special technique for fisheye images. So because of the scarcity of omnidirectional images with highly accurate segmentation ground truth, we would like to appreciate the Woodscape team for sharing the dataset to the research community. We're happy to be part of the challenge and look forward participating in the next challenge. Thank you. So do you have any questions?
Thanks very much, Anho. So I'm just checking the chat for the question. So somebody actually asked if there's any paper for the work. That's actually for the previous one, I guess. So do you happen to have a paper associated? There is no requirement for one here, but do you plan to publish a paper for this, for the work that you did?
We have no plan for it. If yes, I will talk with the team. If is there a request for a paper?
It's entirely up to you. So you can choose to put one on archive. So just to summarize all the things that you did with the clean ablation studies and the things that you explained one by one, how you actually got to that score by adding bits and pieces one on top of the other.
Yeah, and I forgot to mention that our training takes about 18 hours on 2V100. Yes, if you asked.
Yeah, that's great.
Yeah.
Okay, so thanks, and well, so.
Yeah, thank you.
Cheers. So we reached the end of the presentation there. So if you have any questions for the challenge in general, or anything related to the challenge, you can ask now in the chat, or
I have a question. So what do you think is the next step for the challenge? Like you show multiple categories, like semantic and others. Do you have any plan for extending this?
As of now, we don't have any plans or a definitive date on how the next challenge or to do with it. But we do have, so we have withheld the test data. So if you plan to release it, so we'll have to adjust to a different task or altogether. But for example, in the during the challenge, actually, we got an issue there in GitHub relating to combining the vehicles, and we had to redo the labels. So we're actually taking these things there into account. So if there, but for now, we don't have any definitive date or anything for the next challenge.
Yeah, thank you. Yeah, and your comment on privacy was very relevant for the community. Thank you.
Thanks. Okay, thank you all.
Thanks for the chair.
So now we're going to do a 45 minutes break for posters. So please, you can go on the website of the workshop to visit the videos, see the slide related to the papers and posters. And also you can have a chat Q&A session on Discord and interact with the authors. So congrats for the paper and posters. So OmniFlow, human omnidirectional optical flow, detecting low rank regions in omnidirectional images, evaluating the impact of wide-angle lens distortion on learning-based depth estimation, scale 360 layout, revisiting non-central panoramas, and omni layout, room layout reconstruction from indoor spherical panoramas.
Hello, everybody. As it is now 2 p.m. U.S. Central Time, I think it's a good time to begin our next presentation. Next up, we have Dr. Jean-Francois Lalonde. He's a professor at Université Laval. He has a fantastic publication record and track record of very interesting research in the area of omnidirectional computer vision. And cool, he had his screen share right up. And so I'll let him take it from here. And please make sure to post questions on the YouTube live stream, and that way he can answer them at the end of his talk. Go ahead, Dr. Lalonde.
All right, thank you so much, Mark, for the introduction and for the invitation as well. Very happy to be here talking at this workshop today. So just get started. All right, so I always like to start with this example of having this background image relatively empty, and I'd like to add a virtual object such as this bunny to the photo. And, you know, in order to get realistic results, such as this one I'm showing here, I typically have a lot of my talks talk about the lighting aspect, right? We want to light the object the right way, but today we'll take a different look, and we'll actually be looking at the orientation of the object, right? I'd like to make sure that my object is aligned the right way. In short, I want to know the parameters of the real camera, and I want to use those same parameters for the virtual camera that is used to render the object. This is, of course, known as camera calibration, which is the process of establishing the relationship between points in the 3D world and their corresponding 2D projection on the image plane. And this, knowing this is useful in all kinds of tasks, ranging from 3D reconstruction to augmented reality. There are many different ways of doing so, but maybe the typical procedure involves capturing many photos of a known calibration target and running an optimization procedure to recover the camera parameters. This is nice because it gives us very accurate results, but unfortunately, it requires this specific target to be present in the scene, which means we need to have access to the camera, which is not always possible, right? So in the case where it's not possible, then there are techniques that have been proposed to somehow auto-calibrate the camera from the image itself, from a single image. And typically these methods, such as the one I'm showing here, which has been published earlier in 2021, they use cues that are present in the image, such as long lines, right? They will compute vanishing lines and vanishing points from these features. So this is nice because now this works only from the image itself. It does not require any calibration target, but unfortunately, it requires specific cues in the image in the form of lines. So when we're in urban scenes, they're usually present, but if we have a more natural scene, then it's not so much the case. And I'm sure we'll know a little bit more about those with Susanna's talk later this afternoon. And more recently, methods based on deep learning have proposed to learn to predict those camera parameters from a single image using learning techniques, right? And they've demonstrated some success, as I will show later, but they tend, they tend to work on any image, which is the main advantage here. So, and they've learned to pick up cues such as the horizon line, like I'm showing in this example. But unfortunately, they tend to have lower accuracy than the other methods. So we're left with this kind of spectrum of techniques, right? So on one hand, we have methods that are very precise. They yield high accuracy, but they need specific types of images to work. And on the other hand, we have methods that work on any kinds of images based on learning, but they tend to yield lower accuracy, right? So we have to figure out where in this spectrum would we like to be. And I guess maybe our first thought would be, well, I kind of want to be on this side, right? I want to have as high accuracy as possible. But is this always the case? I'm going to claim in this talk that this is not necessarily always the case. You kind of see me coming, right? So we might not always want to be in the high accuracy case, whether it's for all kinds of cameras here, right? I do want to talk about wide angle, lower fields of view. I think this kind of applies in both cases. But here, you know, we don't necessarily want to be always in the high accuracy case. Maybe in applications that are perhaps more qualitative, more artistic, such as virtual object insertion, maybe we can get away with lower accuracy and perhaps even lower accuracy. And the question is, where, right, on this spectrum should we be? And what should be guiding this decision? Well, I'm going to claim that this should be actually linked to the way us humans perceive these images and perceive these results, right? Can we find the technique that will fool the eye, even if it's not perfect quantitatively? If it looks good qualitatively, maybe we've reached a good objective. All right, so the goal in this talk is going to be to try to establish a link between the techniques that we use to calibrate cameras and the way we perceive the results. Okay, we'll try to bridge the gap between those two aspects. So hopefully this is maybe a bit of a new way to consider the problem, right? Which is typically considered as a purely kind of quantitative problem. So in order to achieve this goal, we'll split the rest of the talk into two main sections. The first section, in the first section, I'll be describing a method for a learning-based method for a wide-angle camera calibration that works from a single image. And I'm saying wide angle here, but it actually works on a wide range of fields of view. And in the second part of the talk, I'll be talking about a novel perceptual measure specifically for camera calibration that can help us determine whether our methods will actually fool the human eye after being run on the image. All right, so let's get started with step number one. We'll describe our approach. So we start with a simple image formation model where we have this equation that links together the 3D world coordinates of a point to its 2D pixel coordinates. And it goes through extrinsic parameters in the form of a rotation and translation, as well as this generic projection operator. And here I use this generic operator P to model both the projection as well as the lens distortion that will be more and more present when the field of view gets wider. All right, so I'm just going to sort of wrap those two things up into a single simple P. We'll assume that there's no translation, so we'll just have the translation be 0 because the camera, projection, the center of projection is just going to be the origin. And then let's take a closer look at this rotation. So the rotation will split into two angles: the pitch, looking up or down, and the roll, so tilting sideways, where the yaw, so looking left or right, is assumed to be 0 since there is no sort of global reference frame. Well, we'll just assume that the yaw is always 0. All right, so we have these two parameters. Now let's take a look at the intrinsics. So for the intrinsics, we'll model our operator P using the unified spherical model, which is a model introduced by Ricoh in 2006. And the way this works is that at the center of projection, we'll actually draw a unit circle. And then if we have a point in 3D, after rotation, we'll project it to the center of that circle, and then we will shift that center of projection down by a Xi value, right? And this Xi will tell us how much distortion is there in the lens. And we'll start from this bottom point, trace it back up, intersect the image plane to get our projected point. All right, so this is nice. It's actually a nice model because for actually many different reasons, including the fact that it's invertible, right? So it's simple to add or remove distortion to and from an image. It's efficient. It emits closed form solutions for projection and back projection that can be efficiently computed. It's very simple. It only uses a single parameter Xi that's bounded between 0 and 1. And it's also quite elegant because if Xi becomes 0, then it just boils down to usual perspective projection. All right. So this is the model that we're going to be using to model, to represent distortion and projection in our images. So we'll take some, just visualizing the Xi, the influence of Xi. This is what it does as you vary it from 0 here to perspective to 1. It becomes very kind of curved. And we can also change either the focal length or the field of view. These two are kind of interchangeable. So here I'm just showing the field of view. With this image formation model, we'll combine it with a data set. So we downloaded panoramas from the 360 Cities website, and we combine it with our parameters from our camera model that we can just essentially randomly sample. And that will give us a large data set of regular images taken from seemingly regular cameras, but for which we have the ground truth parameters, right? So the trick here is to use 360-degree panoramas and then render crops based on those camera parameters. And then we have the ground truth, we have the images, we can simply plug them into a very simple, in fact, neural network. There's no magic here. Input image, dense net encoder out for 4 output heads directly, where we have the roll, the pitch, the field of view, and the distortion. And here, what's to note is that we represent the roll and the pitch, the camera angles, as a function of the horizon line in the image. We found that it's actually easier for the network to tie these parameters it needs to estimate, like the tilt of the horizon line, its distance to the center of the image, as a function of features in image space. It's a lot easier for the network to reason about this rather than just abstract angles. Okay, so that's our network, that's our approach. So relatively simple, so far so good. Let's just take a look at some results. First, quantitatively speaking, this is a comparison of the error on the focal length estimation. So here on the x-axis, I'm showing the actual ground truth value of the focal length, and the y-axis is the error. And here we compare 3 different methods. In orange is ours, in blue is the SVA. This is the method based on the lines that I mentioned earlier. Extracting the lines and computing the orientation as well as the focal length and the distortion of the camera. And then the pink one is another neural network that relies on extracting surfaces. Oh, right, sorry, upright is not a neural network. Sorry about that. It's another approach, slightly older. So here in orange, you can see that as the focal length increases, then the error also increases slightly. But so far, our approach is able to work relatively well, and so are the others, to be honest. Just one thing to note, let's just move on to the distortion. So as this is for wide angle images where we wish to estimate the distortion. And as you can see here, as the distortion increases, our method, the error of our method also increases. So not as much as the blue one, by the way. So SVA seems to be performing better on these images. However, one thing to note here, and that's written as a little footnote, but the footnote, as usual, is quite important. Just make sure you read the fine print. And the fine print here is that this method, because it relies on these long lines, it actually does not work for about half of our test set, because our test is actually quite varied. It's got a lot of images, indoors, outdoors, nature scenes, urban scenes, etc. So whenever there are no long lines, then SVA is not able to return an answer. But here we're displaying the results only for the images for which SVA was able to return the answer. Qualitatively, this is what it looks like. So here are some results for urban scenes, and I'm displaying results by showing the horizon line, right? So the ground truth horizon line is in solid blue, and the estimated horizon line with our method is this dashed orange line. And these are competing techniques. The pink one is the SVA, the one that we just mentioned before. And here's another example where our method is able to get quite close, whereas SVA is also not too far. But that's for urban scenes. Let's take a look at some nature scenes now, where cues are essentially not available. Straight line cues are not available anymore. Our method is able to somehow figure out the cues that it needs from these images in order to retrieve a decent answer. Talking about cues, which cues, right? Which cues are helpful? Well, in the case of if there are vanishing lines, the network is able to actually learns to detect them. So we're not telling it to do so, it's just kind of learning it from the data. And here, the way what I'm displaying here is the results of a guided backpropagation with this, the smooth grad version, which essentially is the way of highlighting the parts of the image that are responsible for predicting that answer, more or less. And you can see that it's learning to predict the vanishing lines when there are any, and if there aren't any, such as the case of natural outdoor scenes, then it learns to rely on natural cues, such as the horizon line in these examples. All right, we did compare our method with multi-image calibration methods, the ones that use the checkerboard. And of course, as expected, it doesn't work as well, right? So our method, for example, in this GoPro sequence yields an average error of 2 to 3 pixels of reprojection, whereas these calibration methods, are below the pixel in this case. So that's expected. And this actually brings us back to the question I asked at the very beginning, and it is, do we always need the lowest possible error, right? Can we get away with lower, maybe higher errors, lower precision, but then while doing so, maybe we're gaining flexibility in that we don't need access to the camera anymore. And this is when we started thinking about, oh, let's actually try to establish a link between computation and perception. So let's talk a little bit about that now. In order to establish that link, we decided to run essentially a large-scale user study and chose the task of, no big surprise here, virtual object insertion in order to determine whether humans are sensitive to errors in camera estimation, camera parameters, estimation errors. All right. So in this case, we start with a background image. Since we control our image formation model, we can tweak it as much as we want, right? We can render a background with a certain set of camera parameters, and then we can sample another set of camera parameters and use them to render the virtual object. And those might be different. And we can show them to the user. So for example, here I can have this image, but I can have this other image on the right-hand side, and I can show this pair of images to a person and ask the person to select the image where the object looks better with the background. All right. And the task of the person would be to click on, let's say, on the best image, the best looking image. So maybe here the right answer would be the image on the left. In the image on the right, the virtual object has different camera parameters. And then we can vary the amount of distortion, right? We could say, let's add a little bit of distortion, or let's add a whole lot, and let's see if people can pick that up. And we've also specifically instructed participants to disregard any unrealistic lighting, shadow, or object placement to make sure they don't focus on that, right? Because there's many, many things that can affect the realism of a composite, the realism of a generated image like this. And we don't want them to focus on them. We just want them to focus on the shape, the orientation of the object to tie this back to camera parameters. All right. So in a few minutes, I'll show you some of the findings that we have from this user study. Let's take a look at camera pitch. Pitch is the angle looking up or down of the camera. And here, it's actually not too surprising. So what I'm showing here is on the y-axis is the pitch value. What I mean by that is that's the ground truth camera orientation for the background image. All right. And then on the x-axis is the error that was induced to the virtual object that was inserted. Okay, so right here in the column in the middle, this is where the virtual object has the right parameters. Okay, so in this case, we ask the user to compare two images where essentially it's twice the same object. So on average, people should pick the right one 50% of the time, right? Just by luck. It's essentially a random guess. And this corresponds to the blue, dark blue color in this plot, right? And as the confusion increases, right, then actually, no, this is the sensitivity. So if it goes up to yellow, that means people are able to spot the ground truth all the time. Okay, so we're never confused. So what we see here is therefore not too surprising. So when the error is 0, then essentially we're confused. We cannot pick the right one. And as the error increases, either positive, so basically looking up, or negative, looking down, then the error also increases, right? So meaning we're able to spot the differences more and more. Okay, so this isn't too surprising for the pitch, and it's just kind of two examples. This is the example I just showed you, and this is another one where the ground truth is looking up slightly, and then the virtual object, the camera is looking up even more, okay? And we're able to spot that. But maybe somewhat more interesting and maybe more tied to the topic of this workshop is when we consider wide angle lenses, there's distortion that appear, right? And here we see a non-symmetric response of people. So essentially what we're seeing here is that as the distortion of the background is low, meaning objects are more or less straight, then we can, as soon as there's an error, we really pick it up. On the other side, if the distortion of the background is high and the object it has low distortion, then we essentially not really notice what's happening here. Let me show you what it corresponds to. So here on the bottom right, that means the background is straight. You can see the straight lines in the background, so it's perspective projection. And the ground truth here is straight, obviously. But then when the object is distorted, so it looks curved, then we spot it. All right, people really notice that. So we don't really like to have curved things when the background is not curved. But interestingly, the opposite doesn't seem to be as true. So if I look at the other corner, if the ground truth, the background is curved, but I insert a straight object, most people are fine with it. All right, we don't necessarily want the ground truth object to have the same curve as the background. All right, so that was kind of an interesting finding that came out of the study. And that's one I wanted to share with you. We have a bunch of others in the paper, but if you have any questions about that, I'd be happy to answer. And from this, just quickly wrapping up, we can actually get all of this perception data, and we fit a piecewise linear models to this perceptual data, and we can use to evaluate as a sort of a qualitative. Well, it's quantitative here, but it's actually tied to our human perception. So we have a perceptual measure that we can use to compare different techniques. Okay, so here is a comparison for, let's say, the pitch angle, first one I showed you, where we can compare the different techniques now in perceptual space that really corresponds to the way people perceive these things, right? So we've now established this link I was mentioning before between the computation performed by the neural networks and the perception that are done by the humans once we look at those results. All right, so in summary, I've presented to you a learning-based approach for camera calibration that works for wide-angle images and takes into account the distortion created by the lenses when we start increasing the field of view. And we've tied, again, this to a perceptual measure for camera calibration, which we obtained through a large-scale user study. And with that, I'd like to thank the co-authors of this work, which is actually currently under review, fingers crossed. And thank you for your attention. I'd be glad to take your questions.
Wonderful. Thank you, Dr. Lalonde. If there are any questions, please feel free to post them in the YouTube live stream. In the meantime, I actually have a question. Sure. And I know last year at a workshop, you gave a talk about where you discussed relighting. Yes. In omnidirectional and I'm curious to what extent this small camera parameter estimation error would be noticeable when you try to relight these objects in the scenes that you place them into.
That's a really, really good point, because obviously, you know, the lighting also has a directional aspect to it, right? So there's going to be a main direction of lighting, and if that's off, right, that could be combined with the fact that the object also is off, right? So there's, I guess, an interesting interaction here to explore. Now, to be honest, we kind of, you know, explored them independently so far. So we've done user studies on lighting separately, and you know, assuming that the camera, rather the object was always had the right camera orientation. And then we've done user studies like the one I showed you on the orientation, while the lighting was kept, well, not the ground truth in this one, because we don't have the ground truth for all of these panoramas, but you know, we ask specifically people to not focus on that. I think it'd be fascinating to kind of cross these two things, right? And evaluate the interactions between those two. I'm guessing, actually, so people are actually quite bad at noticing lighting errors. There is this sort of really wide leeway that you have, which is roughly 30 degrees or so, where if you change the azimuth of the lighting by within 30 or something, you know, 30 or so degrees, nobody notices. And for the elevation, it's even worse, right? So the elevation of the lighting, you know, I don't exactly remember the numbers, but it's even worse. So we're actually quite bad at judging shadows. And it seems like in this case, what we found is that in some cases, we're quite bad at judging the orientation or the camera parameters, intrinsics or extrinsics. But in some others, we really need to be on spot. Another example that I didn't have time to talk about, but maybe I'll take this opportunity, is that of camera roll, right? So the roll is this tilt. And if the roll of the background is straight, which is the case for most photos, then it really needs, the object really needs to be straight as well. We pick it up as soon as it's tilted by just a few degrees. However, if the camera, we feel artsy, a little bit artsy, and we take our photos that way, right? You see these things on Instagram and such. But if you feel artsy and you tilt it by like 30 degrees, then there's a much higher leeway. People don't notice if it's like 10, 15 degrees off. So it's asymmetrical. So I would say that kind of combining these two things together, yeah, might reveal cases where you can really make a lot of error and nobody will notice.
That's very interesting. Thank you, Dr. Lalonde. I wonder if that actually might not be a great segue into Dr. Richard's talk next, where he's talking about casual 360 VR photography. And that perhaps, what this tells us is there may be an opportunity to get away with quite a bit without ending up in an uncanny valley when a scene or for a virtual representation. But so thank you, Dr. Lalonde, and I would like to pass. Thank you. Yeah, I would like to pass this over next to Dr. Christian Richard, who has quite the background on within virtual reality and omnidirectional imaging himself, and he's going to talk about casual 360 VR photography today. So with that, Dr. Richard, please take it away.
Thank you so much for the introduction, Mark. It's my pleasure to present our recent work, OmniPhotos, here at this workshop. This work is presented at last year's SIGGRAPH Asia conference, and as I mentioned, I'm delighted to present this here on behalf of my team, comprising Tobias Birtel, who will be graduating this year, Mingzi Yuan, and Ruben Lindros. And the goal of our work is to achieve casual 360-degree VR photography with motion parallax. And so to start off with, VR photography really is a different type of photography. It's about capturing a scene in a way that is more lifelike and more immersive than any existing photograph. So our goal is to capture a scene quickly and casually, and to reproduce its appearance realistically in virtual reality, for example, back at home. So one of the earliest approaches to capture a scene in the type of VR photography dates back to panoramas. So these capture the appearance of a scene in all directions, but generally they appear quite flat because there's no depth cues in there. Omnidirectional stereo panoramas introduce binocular disparity, so they have two different views, a left eye view and a right eye view panorama, and this creates stereo vision that gives us depth cues. So that's really quite nice. And these techniques have later on been extended to videos using multi-camera rigs, and that is currently still the standard format for 360-degree VR video. However, these approaches only provide stereo views with binocular disparity, so they miss some important depth cues. In particular, motion parallax is super important, because as we move our head, we want to see a different viewpoint of the world. This is a really important depth cue for the human visual system that is missing from these existing techniques. So a good way to get motion parallax into panorama is to try to reconstruct some texture geometry. But this is actually very difficult, particularly for general scenes. 3D reconstruction is far from a solved problem. Some sort of simpler approaches look at layered depth panoramas. So this is, for example, using multiple layers in a spherical setting where you have some layers for foreground objects such as people, then you have medium-term objects and far background objects. One can also extend stereo panoramas with depth, so estimating depth from the omnidirectional stereo to enable 6-degree of freedom experiences. And the area with the most work over the last few decades is image-based rendering. So this is a combination of 3D reconstruction and rendering new views based on the input images that sort of tries to overcome the limitations of 3D reconstruction to create highly plausible and really good-looking novel views, such as this example here on the right-hand side. This is from Google's Welcome to Light Fields paper. So this is a demo you can download from Steam, for example, and try it out in your home. Now, 3D reconstruction would be the ideal solution if we get it to work well in all cases. Several works are pushing this forward with multi-view stereo, for example. Here on the right-hand side, we see a technique called casual 3D photography, And this works really well indoors for highly textured scenes such as this one. You can see a lot of motion parallax. It looks really nice. So this is fantastic. But these techniques, as we'll show later in this talk, they don't work well outdoors or in other areas. What can help is if one has a depth camera, and a lot of smartphones and tablets nowadays have depth sensors built in, so they can take advantage of that. If that's not available, then also one could use monocular depth estimation. And there's a few really cool papers out there at CVPR last year, for example, on the 3D photography from a single photo. However, what I'm personally more interested in is 360-degree scenes. I want to capture everything around us. And so we need to get depth maps for full 360-degree images. And this has seen quite a lot of progress over the last few years. But what is missing still is a really high resolution depth that is needed for VR rendering. In VR rendering, you would need a resolution of about 4K to match the pixel resolution of the display of your VR headset. But 4K depth maps are far from being possible nowadays. We have seen a lot of progress over the last few years in learned view synthesis and neural representations. This all started with learning how to blend the input images in a better way, then moved on to multiplane images. So these are sets of parallel layers that are semi-transparent to reconstruct objects. This looked really, really great, and was then extended to multi-sphere images, including some of our earlier work from last year, multi-sphere images, so reconstructing 360 scenes all the way around us. And a lot has happened in neural rendering, neural representations in particular, since the beginning of NERF, the neural radiance fields kicked off last year. We have seen so much progress and amazing results. The problem is this looks fantastic, but it takes half a minute to render one image. So this is not feasible for VR experiences right now, although we have already seen there's some work on Archive that explores various ways of speeding up the rendering to real-time frame rates. So this is a very quickly moving area, and we haven't seen the last of it yet. So, but our goal was to make casual 360-degree VR photography possible. And to do that, we looked at the full VR photography pipeline from capture over reconstruction, representation, and to rendering. And so to achieve our goal of making this whole endeavor casual and accessible, we had to innovate at all of these stages. So we wanted to make the capture really fast, less than 10 seconds. It should be casual and easy. You shouldn't need any particular multi-camera rig. So just an off-the-shelf camera should be sufficient. On the reconstruction side, we developed a robust approach that is tailored for image-based rendering. And for that, we're introducing a scene-adaptive proxy geometry that I will go into in a bit more detail later. On the representation side, we have created a hybrid representation that uses this proxy geometry, the input images, and correspondences, so optical flow between the input images. And this representation turns out to be quite robust and reliable, and we have tested it on more than 50 images, 50 data sets. And what was important for us is to achieve real-time VR rendering with really high quality motion parallax and a very large head box. So you can move your head side to side 1 meter, which is much bigger than existing systems. All right, so let me go into these different stages one by one. Let's start at the capture side. And our starting point was to use an off-the-shelf camera, and very fitting for this workshop, we used an off-the-shelf 360 camera. So these cameras have a lot of advantages. They see in all directions. They allow more robust camera pose estimation. And the increased field of view is also what makes this larger head box that I mentioned possible in the end. Because with this, we can actually capture the whole hemispherical view in front of a person. And we put this camera on a rotating selfie stick. And with that, we can actually then rotate the camera around quite quickly. So this is our idea of how we can capture a range of views of a scene in very little time. So we found from the data sets that we have captured that a revolution is on average 1.7 seconds. And what we need is just one revolution of this video. And from that, we can reconstruct VR photographs. So in the best case, one can get away with just 2 seconds of capture time to capture a scene in 360 degrees to achieve immersive VR experiences. Another benefit of the selfie stick is that it enables smoother and more repeatable camera motion than what if one were to do this manually, for example, holding a camera on a stretched out arm and rotating on the spot. Okay, on the processing side, we have 5 stages in our pipeline, and these are the first 4. We start by stitching the video as it comes from the camera using the included software, the Insta360 Studio. software to stitch stabilized 360-degree equirectangular videos. We then reconstruct the camera pose using OpenVSLAM. And for this, we found it useful to do that in 2 stages. So in the first stage, we are just reconstructing a sparse point cloud of the scene. And in the second stage, we're then registering the camera to that sparse point cloud. And this enables us to reconstruct a much smoother, more robust and accurate camera trajectory for the scene. In the third stage, we are selecting one of the loops from the captured video. For most of our data sets, we captured multiple loops because it's easier to swing around. Even in just 10 seconds, you can get 4, 5, 6 different swings in. What we need is just one swing. And this is currently still the only manual step in our pipeline, but we're working on this right now to automate this as well, so that the entire processing pipeline can be automatic. Now, the fourth step is to compute correspondences between these input images. So between adjacent video frames, consecutive video frames, we compute optical flow using DIS flow and OpenCV, or using FlowNet2, using a deep learning-based flow-based technique. We can use any existing flow method, really, and we work with that. And the fifth step is a new approach to represent the scene as a proxy geometry that is adapted to the point cloud that's reconstructed from the SLAM reconstruction that we do. So I mentioned we use OpenVSLAM to reconstruct the sparse reconstruction of the scene. And what you see here is a few thousand points that were reconstructed from one particular data set. We then start with a spherical mesh and formulate an optimization to deform this mesh accordingly to the 3D point cloud in a robust way. Now, we need to do this in a robust way because not all the points are reliable. There's about 10 to 20% outliers in this point cloud. But let me go into a bit more detail here, how we do this fitting. We formulate this in energy minimization that we optimize using nonlinear least squares. So there's multiple terms in here. And essentially what we're optimizing is for the vertices of the spherical mesh to move in the radial direction, inwards or outwards, such that the triangle faces of the spherical mesh align with the 3D points. So we have a robust data term for this. We have a smoothness term that we are applying across the sphere to get a smooth reconstruction that doesn't have any sharp edges in there that might show up in the view synthesis result in the end. We're having some special terms to deal with the poles, and a prior term for areas where we don't have any features reconstructed, such as in the blue sky, for example. Now, for the implementation, we're optimizing all of this in inverse depth. This better regularizes the scale of variables than if you were working with depth directly. To implement this robust data loss, we use scale tuber loss, and this handles the outlier points really well. And as another detail, we are formulating residuals in a normalized way. So we're dividing the residual A minus B by the sum of A minus B, so that the whole reconstruction is actually invariant to the global scale of the scene. And finally, we're optimizing all of this with Ceres, and the output is what you might also think of as a spherical depth map with a quite coarse resolution of only 160 by 80 pixels. So this is quite coarse, as you've seen, but it will also show you the high quality of results you can still get out of this. Now, this brings us to the representation. For this, we have our posed input images, so the camera poses for these 360 images. We have pairwise optical flow, and then this reconstructed proxy geometry. On the rendering side, we then generate new views on the fly using GLSL shaders. And for that, we're generating every single pixel independently in parallel. Now, to do that, we're looking at one particular pixel here, for example, this green circle, and see where that pixel projects onto the proxy geometry. Now, the point on the proxy the direction to the through the pixel tells us which of 2 input views are most suitable for interpolating this view. We can find, based on the direction, one image that is just to the left, which is this blue 360 view, and on the right-hand side, which is this orange 360 view. We can then reproject the proxy point into these 2 views, and this gives us an idea of what the color of this point that the green pixel is looking at might be. So we can blend these 2 colors together to synthesize the color of that pixel. So that is the basic version. Now, this works great if the proxy geometry is accurate. If it's, for example, matching to some buildings, this works fantastic. It's just linear blending between the reprojected pixel colors, and that's all great. Now, this is not always the case. Sometimes the actual scene is at a different distance to the proxy. For example, there might be a fine fence, for example, or there might be some reflections in a scene. And so if an object is closer, this rectangle here, it projects to quite different locations, potentially in the 360 images. And we compensate for this using the optical flow that we have pre-computed. So we can look up the locations and look up the optical flow there and then interpolate and compensate for this depth error, essentially. So we call this view-dependent flow-based blending. And all of this is possible at real-time frame rates, more than real-time, 90 frames per second and more in a VR headset. Now, I would like to show you what this looks like. So I've tried giving a live demo before, but this does not play well with live streaming. So this time I have pre-recorded the live demo for you. And I would like to play that for you now. All right, welcome to Bath. This is an Omni photo of Bath during the first lockdown in 2020. As you can see, it's entirely empty. There's no people around, so this is a very rare sight for Bath, which is usually very popular with tourists. You can see it's a 360-degree view of the beautiful Roman baths and Bath Abbey. You can see motion parallax cues that I mentioned. As in left and right, you can see more or less of buildings behind other buildings. You can also see more buildings behind there. And you can also see the reflections in the window move according to my head pose. So this gives us very high quality motion parallax depth cues. And all of this is achieved with a very simple proxy geometry. This is what the proxy geometry looks like. So this visualization shows you sort of how smooth the proxy geometry actually is. You can vaguely see the floor, the ground, and the buildings around itself. But when I switch back to the visual images, you can see that the buildings are definitely much flatter and have sharper edges than the proxy geometry can represent. But in combination with the flow-based blending, we can compensate for any mismatches in the proxy geometry. So you can see that even for the bench that is not actually represented in the proxy geometry very well, we can still get plausible views with motion parallax as I move my head left to right. Okay, I will speed ahead a little bit to finish regular on time. Here's a comparison with some previous methods. Parallax 360 on the left-hand side only enables limited motion as the camera moves through the scene. Megaparallax, some of our earlier work, introduces distortions as the camera moves, and you can see that our Omni photos produce the most realistic synthesized views here. Here's another scene. It's quite a complex scene. You see a lot of people, and that's now the benefit of a fast rotating camera, is that the people don't move very far in 2 seconds, so we can actually reconstruct this quite well. And again, you can see our reconstruction is more realistic than the previous two techniques. Now, we also have some comparisons here to 3D reconstruction-based techniques that I mentioned. So on the left-hand side is the casual 3D photography approach, and you can see that it works really well for the hut and the stairs, but it struggles with the background where you have a tree with very thin branches and some uniform colors, and this is really cases where 3D geometry fails. Our approach fails a bit more gracefully there. You can see that we can interpolate and blend the images there much better. You still see some ghosting artifacts, and this is because this data set does not contain enough, a sufficient number of input images. Here's another comparison for an indoor scene where the 3D reconstruction tends to work quite well, and you'd have to look quite carefully to find incomplete geometry in the casual 3D photography case, whereas in our case, because of the insufficient number of input views, we see some flow warping artifacts here. But our technique really is designed and works better outdoors. So here are a few more results that I would like to show you. Overall, we make 30 datasets available that you can try out. We have a demo that you can download as well, where you can view these datasets on a desktop or in your VR headset. And all of these were captured with a swinging, rotating selfie stick. Some of them also captured handheld. And they were captured all over the world in the before pandemic times. What you can see here is really also the nice reflections on the left-hand side that are really difficult to reconstruct with 3D reconstruction. And also this scene of a field where the very fine geometry of the grass would make it really hard to actually reconstruct this in 3D. Okay, let me talk quickly about limitations. So perhaps one of the most obvious ones is that we don't allow any vertical motion. However, in practice, we don't think that is a big problem because for seated VR experiences, users naturally keep the head at roughly the same height. There's some other limitations due to the specific approach that we proposed. So if the proxy is not accurate, we can see some warping artifacts, for example. So here the proxy stretches from the tree in the foreground to the tree in the background. and that doesn't represent the scene very well. So you can see warping artifacts as the view is changed. We also rely on optical flow being accurate, which is not always the case. So we found some issues when there's strong edges next to uniform colors. And we also observed some stitching artifacts in the software and proprietary software. Yeah, that's just something to be aware of, I guess. So in future work, currently the memory footprint is quite high still of OmniPhotos because we have about 100 images and 200 optical flow fields. But this can be compressed quite dramatically to only 1/4 gigabyte using 7-zip, for example. And more compact file formats would really help here. Something that's really interesting is to look more into editing VR photographs. So for this work, we only focused on capturing a scene and reproducing it as it is. But really, sometimes you want to relight a scene. You want to change the time of day, or you want to insert virtual objects, remove some people that are standing in the way. There's a lot of things that are still to do. And finally, it'd be really interesting is to combine the proxy and the flow together and sort of optimize this actually jointly, perhaps using a differentiable renderer to maximize the quality of the synthesized views. So in conclusion, I've presented our work OmniPhotos, a casual approach for 360-degree VR photography. It's the fastest, casual, and most robust capture technique for real-world VR experiences for general end users. Currently still the fastest technique, just need one swing of the camera. And we have improved the visual quality using the scene adaptive proxy geometry and proposed an approach for real-time VR rendering of immersive 360-degree environments. Our code is completely available on GitHub. Our datasets, 30 datasets, as I mentioned, are available as well, and a demo that you can download pre-compiled to try it out on your own machines. And I would like to close by thanking my university and institution and sponsors, and would now be happy to take your questions.
Wonderful. Thank you, Dr. Richard. If we're looking on the YouTube live stream, Dr. Lalonde actually has a question. He says, very cool work. Thank you for the presentation. And I'm wondering, are you worried about motion blur as the camera is spun around? Sounds like this would limit the speed of capture. And to add my own piece to that, I would also imagine it would impact the flow estimation. So yeah, that's a very interesting question. What do you have to say about motion blur?
It is a very interesting question. So what we found is that you need to set the exposure time sufficiently low to avoid motion blur, or to minimize motion blur, let's put it that way. If I remember correctly, our exposure time was 0.002 of a second, which corresponds to about, I think, 1 or 2 pixels at most at 4K resolution. So this is small enough that it is not objectionable, but it is a trade-off. If it's very dark, then this exposure time would not give you a very nice video. So I guess that is another reason why it works best outdoors, because indoors you might not have enough light for this.
Got it. Thank you. Thank you. Yeah, and it looks like Sing Bing Kong also commented that especially if the scene is indoors, low light settings, he imagines the motion blur is a bigger factor. And Pierre had a question. Is there a data set with ground truth depth data, I guess, that would be relevant as part of this?
So I'm not aware of any outdoor data set. There's a range of indoor data sets that were mentioned by the earlier speaker in the workshop. Outdoors is certainly a problem that we're also exploring right now. It's difficult to get ground truth. The closest I think you can get is a reconstruction from multi-view geometry. But that needs to be filtered carefully because you don't want these outliers there for your ground truth evaluation.
Of course. Well, I actually had a question as well, specifically regarding the, if I understand correctly, you deform a sphere in order to create this, what was the term, the proxy, the proxy reconstruction.
Yep.
Now, what effect does that have when you have very, very far away parts of the scene? So things like sky in the background, typically you don't have to worry so much about parallax, but if there's strong depth disparity, or like depth edges, do you find that is a failure of the genus 0 mesh prior?
That is a very good question. As you mentioned, things that are very far away, it doesn't matter if the depth is very accurate because the disparity that you get is quite low in the end. I think what probably breaks sooner is the SLAM reconstruction that will just not triangulate points that are very far away at some point because the triangulation angle is too small. So I think our points were at most 10 to 20 meters away in the reconstruction. Not that there were probably points that were further away, but those were not reconstructed with that pipeline. Could probably improve it. For our sphere reconstruction, we're optimizing an inverse depth space, so that should make it sort of quite nicely uniform in a perceptual way. But yeah, it's a bit tricky.
Awesome. Well, thank you very much again, Dr. Richard. We appreciate you having you at our workshop this year. Okay, so I think our next presenter is in the room. We have Senthil, I apologize in advance, Purushwalkam. Am I saying that correctly?
Yes, that's good enough. Yeah.
Okay, Senthil Purushwalkam. He's a PhD student at Carnegie Mellon University. Today he's been presenting work that he did along with one of our originally booked speakers, Dr. Kristen Grauman, who couldn't give her talk today. And so Senthil will be presenting in her stead, and I will turn it over to him. But before I do, I will say that it's always very interesting to have a talk like this one coming up, where we're going to be talking about the intersection of audio and video. And in this case, it's very relevant for floor plan reconstruction. So Senthil, please take it from here. And thank you.
All right, thanks, Mark, for the introduction and having me here. I hope the screen looks fine. Let me just also turn on audio sharing. Okay, so my name is Senthil, and I'm a PhD student at Carnegie Mellon, working with Abhinav. And I'm going to talk about this project called Audiovisual Floor Plan Reconstruction that was done in collaboration with Facebook AI and Facebook Reality Labs. So let me start off by walking you through this toy example of a walk through an active household, where let's say a camera starts at this position recording and moves through the household in this way. And this camera is obviously capturing a large part of the household, but it's also not capturing a big part of it that was never explored. And using existing methods like SLAM, we can reconstruct these visible areas very accurately. So here's like a method called active neural SLAM that explores the environments, captures RGB frames, and reconstructs this 2D map. But what you can also see here is that this little red agent that's moving around in the environment needs to explore every corner of the household before it can construct a full map of the whole environment. And this is obviously very inefficient. And so the way we want to fix this problem is that we want to use additional cues that are available in the audio that occurs in our environments in our everyday lives. So to motivate this, for example, imagine that a person walks through the same trajectory, but he hears the sound of a flush on his right as soon as he enters the home. And hearing the sound basically tells you that there is room there, there's a room there, and it's probably a bathroom, and basically that there is some space there. And as you walk through, you might also hear other sounds like a kitchen, someone cooking there, and you might again make an inference that there is a room there, which is a kitchen, and so on. So we basically want to want our models to take advantage of these cues and also try to estimate the floor plans of the regions that are not visible in the visual stream. And so that would look like estimating an interior map like this, where we're estimating all the regions that are inside the home and differentiating it from the boundaries of the homes. And then we also want to take it one step further, where we want to classify these regions that we estimate as interior into one of n categories. So like things like kitchen, bathroom, bedroom, living room, and so on. And I'll talk more about what these maps look like and how to represent them. But before that, let's look at what information we can actually gather from the sounds that we capture in our houses. And the first piece of information that's probably very intuitive to understand is that if you listen to a sound in a household, you can probably very strongly have an inference about what kind of room exists there. So listening to a telephone probably tells you that there is a living room in that source location. And then listening to a faucet, for example, tells you that there's either a kitchen or a bathroom in that location. And something that we do not perceive, but we can take advantage of with our models, is that as these sounds propagate through our house, they also reflect off the surfaces, the walls and the ceiling and things like that. And just by capturing these patterns of reflections, we can probably estimate the geometric structure of the rooms that where the sources are located. And so this is something that we want to take advantage of in our households. And so more concretely, the problem looks like something like this, where we have a video with some audio also being recorded in the houses. Let me try to see. Okay, so you can probably hear someone brushing their teeth. There's an alarm playing in the background, and you're just walking through this household. Lower this. And the goal is to basically take a video like this and estimate a 2D binary map where the positive pixels represent the areas inside the house and the negative pixels represent areas outside the house. And we also want to estimate another N channel map where each channel is representing one specific room type, like a living room or a bathroom or a kitchen. And so there are two parts of this that I will go through. One is how do you gather the data required for addressing this problem, training and testing. And the second part is the actual model itself and how do we take advantage of the audio. So the first part, I'll talk about how to generate the RGB sequences first. And obviously, it's very difficult to go to homes of people and collect different sequences of videos and have different audio sequences playing. So we do this in simulation. And we use this data set called the Matterport 3D, which you probably heard of in the previous talks, where they basically collect dense scans of 85 home environments. And in addition to the RGB scans of these environments, they provide you with depth maps and they provide you with semantic labels of the room types associated with each of these regions. And they also annotate the objects located in these different 85 homes. So we take this data set and in conjunction with the habitat simulator, we can generate these RGB sequences that look like this. And we basically sample random trajectories of different lengths through these homes and generate these RGB sequences. And that serves as the RGB part of the video. And the other part that we need to generate is the audio. And that again comes from a different data set called the Sound Spaces data set. And that's basically a data set that was collected by people at the Facebook Reality Labs and FAIR. And what they do is in each of these Matterport environments and some other replica environments as well, they sample a dense grid of locations on the floor. And so in this grid, if you place a receiver at any location and a source of sound at any location, the dataset basically provides you an impulse response for this pair of source receiver locations. And the impulse response basically captures how the sound propagates through the environment as it reflects off walls, reflects off different materials, and so on. And this data set also provides you with this omnidirectional impulse response. So you can actually simulate it, and you can also like turn your agent around and make it realistically move around. So the way you use these impulse responses is that, let's say you have a receiver over here, which is either your camera or your recording device. And then let's say there's a sound here in the environment that's playing an audio clip X. And the sound that's perceived by the camera, Y, is different from X. And because it's reflecting off walls and there are probably obstacles in the way. And that audio that is received Y can be basically computed as a convolution of X with the impulse response from this data set. So the question is, where do we place these sounds and what should these sounds be? And that for that part, we basically split it into two different settings. The first is called the device generated audio, and the second is called the environment generated audio. So in the device generated audio, it's a setting where the agent or the camera is moving through the environment, but also is emitting a sound as they move through. So in this setting, basically the receiver and the source are at the same location. And you're basically sending out sounds and you're recording it again to see how it reflected off different surfaces. And the sound that we send in this setting is this frequency sweep, which has some nice properties and allow you to capture the reflections, the distance between the reflections very easily. And in the environment generated setting, it's the more realistic setting of everyday households where there are sources of sounds at different locations in the house, and they're occurring because of the objects that exist in your house. And the objects are closely tied to the room types where they exist. So to simulate this setting, we basically download a bunch of audio clips for different everyday household objects like dishwashers, showers, the flush of a toilet, people brushing their teeth, and so on. And we place them in the semantically correct room. So someone brushing the teeth would always occur in the bathroom, and someone maybe running a dishwasher would always occur in the kitchen. And then we can basically do the same thing where we convolve with the impulse response and generate these realistic audio clips for the videos. And so here are some examples of what the videos look like. So this is the first setting where it's the device generated setting. So we send out the frequency sweep. Okay, and the next one is the environment generated setting where, so we're starting in this kitchen here, and you're going to hear the sound of a blender, but as we move to the living room, you're going to start hearing the sound of a telephone ring in the living room. Okay, so those are the RGB and audio sequences that we work with. And the next piece of information that we need to train and test our models is the ground truth targets. And that again comes from the Habitat Simulator. They provide us with these top-down floor plans, binary floor plans. And because we are sampling our trajectories, we know the locations of the agents at each location, each time step. So we can simply crop out an area around the agent at each time step. And this area, for most experiments in the paper, we choose it to be a 40-meter square area around the camera. And we crop that out and then rotate it to align with some canonical frame, which we choose to be where the agent is always looking left. So this is basically the ground truth map that we work with. And given an RGB and audio clip, we want to estimate this binary map. And so the model that we work with is something like this, where it takes in the RGB frame, and we extract features using a couple of residual blocks, and followed by average pooling to consolidate all the information. And then there's an upscaling layer that extracts a 32x32 feature map. This feature map is passed to a UNet model, which basically downsamples and upsamples the features to give you the final 64x64 classification probabilities of the interior locations. And so in this map, the agent is supposed to be in the center looking left, and this is the area around it that it's estimating. And so this is for a single frame. And to extend this to the multi-frame case to use information in the whole video, we basically do the same thing where we extract independent residual block features plus the upscale features. So this gives you a feature for each frame. And now each of these frames are in a different coordinate reference coordinate frame, because in each of them, it's assumed that the agent is pointing left in the ground truth. So to align them in a common coordinate frame, we basically pad them and translate and rotate the features in this padded region according to the motion that happened in the video. So from the first frame to the second frame, the camera moved forward. So in the features, the first frame is at the center. In the second frame, the features of the second frame move to the left because the agent is moving forward. And then you turn 30 degrees left. Let's say you turn 30 degrees left. So you rotate the feature in this 2D plane by 30 degrees. So these three features are now aligned in a common reference frame of the first time step. And so you can use your standard sequence models on this sequence of frames. But because we want to model bidirectional relationships where we want the last frame to contribute to the time step one, we want the time step one to contribute to the last step. And so we use just self-attention layers at this stage where we basically consolidate information from all the time steps using self-attention. And I won't go into the details of that, but that just gives you the same n feature maps for the n time steps. And you can continue doing the same unit architecture at this point, where at every intermediate stage, you apply a self-attention followed by a unit encoder, giving you your final features. And at this point, you can apply the unit decoder and get an estimated interior map for each time step. And the information from all of these interior maps are aligned because we did the alignment step here initially using the padding and translation and rotation. So you can just pool these predictions using a max pool or an average pool to get your final estimate for the full trajectory. And so this is the final prediction if you're using just RGB sequences. And now to add in the information from the audio, it's basically a multimodal model now where we have one stream processing the RGB using the residual blocks followed by a unit, and the other stream processing the audio where the audio clip is passed through a series of convolutional convolution layers, rectified linear units, and pooling layers, followed by a similar upscaling layer, and again, unit encoders here. Now, at this point, to merge information from both RGB and audio, we concatenate the features from the RGB intermediate layers with the audio intermediate layers. And these concatenated features are passed to the decoder. And so this prediction here now comes from both domains. And it's using information of both that's encoded both in the RGB and audio. So the final full sequence model that we call the AV map model in the paper basically takes in the sequence of RGB frames and sequence of audio clips, processes them independently using the unit plus self-retention encoders, concatenates the intermediate features, and then applies the decoder here, which gives you the estimates for each time step. And then those are pooled to give you the final prediction. And so now, so far, I've only showed you how to estimate the interior maps, where you get one map for each time step and you pool them to give you your final prediction. But the extension to include the room map, where you have the n-way classification, is again pretty straightforward, where instead of a one-channel output, you have an n+1 channel output now, where the first channel does the interior map prediction and the remaining n channels do the n-way classification of room types. And the first channel has a loss of the binary pixel-wise classification using our ground truth. And the remaining n channels do a softmax cross entropy to classify the right room label using the ground truth again from Habitat Sim. So this is the whole model, and we train it using these two losses. And then the product of these two gives you this map that basically has both interior estimates with the correct pixel-wise room labels. So I'll show you some results now using this, so these are the cones are the camera positions, and it's moving through this trajectory here. And the cyan pixels are the ones that are directly visible to the camera. So it should be very easy to estimate those regions. And the green regions are the ones that are estimated by our model as interior to the home. And you can see that it's able to estimate areas behind the camera, to the right of the camera, figure out some walls. And this is basically the 2D projection, 2D drop-down projection of the same prediction, where the green pixels are the true positives that are interior and predicted as interior. The black are the true negatives, so it's exterior and predicted as exterior. And the red is the false positives, so it's actually exterior, but was predicted as interior. So you can see close to the boundary, those errors occur. And then blue are the false negatives, which is actually interior, but was estimated as exterior. And then, so this is a baseline model that we compare to, which is basically state of the art using just RGB, where it tries to estimate beyond what is actually just visible using just the structure of the environment. So if there's a wall, you can probably estimate that there's more of the wall ahead and so on. And again, we can do much better than this because our audio is able to capture more of the free space area around the camera locations. And here is another example where the model is able to predict areas behind obstacles, behind the camera in a different room. And then here is another example where it pretty much captures the whole room using audio cues. And in terms of quantitative evaluation, you can see here that we compare to very naive baselines, like just predicting everything as interior or just using the visible region, but using extra depth information to estimate the layout of the room. And then this is the baseline that uses RGB and tries to hallucinate a little more area around that. And the last three columns basically show you different variants of our model. One is that use a model that only uses the RGB. The second is the model that only uses audio. And the third one is the combination of both. And as you can see here, using both obviously gives you a big improvement over all the other models. And this is the pixel-wise classification accuracy of the interior pixels. And then this metric basically measures the accuracy of our model around the edges by measuring the average precision of the edge predictions. And again, here you can see that our audio-visual model can actually get a big boost from using both audio and visual cues. Okay, so the last part of our model was using the estimating the room classes. And here, what we observed was that using RGB for very short sequences of like, let's say 4 or 5 steps, RGB only can provide only provides very little information. So classification goes almost wrong in most cases, because these could be situations where you're transitioning from one room to the other, or you're just facing the corner of a room, facing the wall. It's very hard to make estimates about the room types. But as you can see, audio actually gives you a lot more information about room types here, and you can estimate more of the rooms correctly. And here are some more estimates. These are using both audio and vision. And even quantitatively, we see that audio does much better than using just RGB. Just audio does much better than using just RGB. But adding both audio and RGB again does better than both. And here are some videos of the maps being predicted online as the agent is moving through the environment. So here you can hear a person typing on the keyboard, and there is a telephone ringing in the background in a different room. And then the next video will show you the device generated setting, where you will hear the frequency sweep, which will be a little loud. Okay, so I'll just stop with this video playing and maybe mute it. And I can take any questions if there are.
Thank you, Senthil. There's a bit of a lag on the YouTube live stream, so it's possible some questions may come through as the stream up to the presentation. But I had a question, perhaps to kick it off, and that's, are there any sorts of rooms that or structures that provide some major failure cases for this? Because I can imagine, I mean, in the extreme case, like a theater that is explicitly designed to dampen sound. Is there anything along those lines where you really see the RGB becomes much more necessary, or are the data sets not, are they too limited to be able to test this at the moment?
So I think the simulation might not be accounting for that. So because Matterport doesn't actually have annotations for the material types, if I remember correctly, the way these simulations were done was that they assume some standard material for the walls, and then based on the object types, I think they add some more materials and they simulate it. So it's not entirely realistic, and to the extent that I'm guessing theaters wouldn't have like very dampened reflections or something like that. But yes, it would be a problem if those things existed, because you would have to additionally model that. But I think the way you would end up modeling that is that the objects occurring in a theater would be correlated with having zero reflections. So you could pick up on these other sort of relationships where if there are zero reflections and there are sounds of a theater, then it is a theater now. You can be more confident about it, and you might have trouble estimating the walls, but you can still estimate the semantics of it.
Got it. Thank you. That makes sense. I'm just looking at the live stream. So I have one other question, perhaps, if nothing is coming in at the moment, and that is really an application. So this is all simulated data and all simulated experiments. Where would this be most applicable, and how can you test reconstruction accuracy on, let's say, like, a headset? Is it possible without having the some ground truth on the materials or some baseline for what the room should look like?
Yeah, so in terms of testing, I'm guessing that you would have to put in some resources to do the initial testing in real world environments. But in terms of application, I think there are the slide that I skipped over, which is basically augmented reality, where you can having realistic simulations of augmentations in the environment requires you to know about the extents of rooms, the kind of room you're in, kind of room the adjacent room is, and so on. And those things you can very easily gather from audio. And things mounted on the augmented reality headset could capture the audio in an omnidirectional way and so on. But even things like assistive technologies for like blind people who have trouble navigating their own homes where they need to go to the kitchen. So having like a headset that knows where the kitchen is, how far it is, how big the kitchen is would really help. And even things like a Roomba robot that would just go around cleaning your home, knowing that there's a kitchen somewhere, how big it is, being able to estimate the extent of it much better, and being able to interact with you in a way that you can ask them to go clean the kitchen would be, they would know where to go basically if they know the floor plan and they know what a kitchen is exactly.
Would the audio have to be in the audible range? I'm just picturing, you know, all those videos of Roombas scaring the heck out of dogs and animals and stuff with the, you know, imagine a high pitched frequency sweep or something wouldn't help. So, and I'm sure for humans, like I have a small child and she's terrified of my Roomba. Would that be problematic? How would you resolve that?
So, I mean, it doesn't really have to be in the audible range, but if you're using sounds that naturally occur in your house, then you don't need to add anything where you're just listening to a dishwasher and realize that there's a kitchen there. But if you're doing the device generated setting, technically you don't need to do it in the audible range because like things like ultrasonic sound are actually much more useful for estimating distances. But we just chose to do it in the audible range here, but it still goes up to the borders of that. Like it goes from 20 hertz to 20,000 hertz. Yeah, you can do it in the ultrasonic domain, but what I've heard from others is that it's too expensive to implement that in like on devices.
Got it. Well, thank you very much again, Senthil. Appreciate you speaking at our workshop today.
Thanks for having me.
Of course. At this time, we're going to take a 15-minute break, and then we'll come back for the last set of invited speakers and the last two oral presentations. So we'll see you all in 15 minutes. Thanks.
Hey, how are you?
Hi.
Hey. Good to see you.
Nice to see you.
So I think we have a few more minutes left. We kick it off.
Yes. So you are chairing the session, or are you chairing the session?
Yeah, so together with Lee, who's also already dialed in.
Good, good.
Hello, hi.
Hi. Can I try to share my screen, or then I can stop it?
Yes.
Go ahead. You should be good to go now.
So can you see my screen? I think it's...
Yeah.
Yes.
Okay, so
good.
I'll
Do you
stop
want to
sharing.
go in full screen mode? I mean, right now
Yes,
we see.
I will. Give me 1 second. Give me 1 second.
Yeah, that looks good.
Is it okay? Should I stop sharing now, or do you still want to show something?
No, we don't have any slides
Okay.
to show, so we can. Yeah, let's just start with this one.
Good.
Yep. Yeah. So welcome back to the session in the OmniCV workshop, the last session in the OmniCV workshop. I'm Jan Michael Frahm from UNC Chapel Hill and Facebook, and the session is I share the session together with Lee Guan. Lee, do you want to say? Oh, you're on mute.
Thank you, Jan, and welcome back to our afternoon keynote session. I'm from UNC originally as well, and right now I'm at
Wimpax AI Research based in Seattle. Yeah, I'm honored to be the host for this session with Jan. And now giving back to Jan. Thank you.
Yeah, so our first speaker is Susanna Kukalova from the Prague Technical University. So it's our pleasure to have her here. Susanna is known for her work on minimal solvers, camera geometry, various applications of Gröbner basis. And she's been doing great work since many, many years. We're really happy to have her here. And she's won various awards, multiple best papers at ACCV, a Young Researcher Award from the European Research Council. So it's a great pleasure to have her. And with that, Susanna, I hand over to you and looking forward to your talk.
Thank you, Jan. So thank you very much for the nice introduction and for inviting me to talk at this workshop. Today, I will give you a brief overview of methods that jointly estimate camera geometry and radial distortion. Unfortunately, in 20 minutes, I cannot go much into details. Therefore, the goal of this talk is to introduce fundamental concepts and to point out current state-of-the-art methods. Camera geometry problems like relative and absolute pose estimation are core problems in computer vision with many applications, for example, in localizations, 3D reconstruction, SLAM, and autonomous driving. Camera geometry solvers are usually used inside ransack-style hypothesis and test frameworks, and here the number of samples that needs to be tested exponentially grows with the number of points used for the estimation. For efficiency, it is therefore important to employ minimal solvers that generate solution from a minimal number of point correspondences. For example, the minimal number of 2D to 3D point correspondences necessary to solve the absolute pose problem for a calibrated perspective camera is 3, and the early solver dates back to 1841, and since then it has been revisited several times, and this solver is well known as P3P solver. Another example is the well-known 5-point relative pose solver for perspective cameras, where we have really well-known and efficient solution by Nister. The P3P and the 5-point relative pose solvers for calibrated cameras are very efficient, and therefore they are used in many applications. However, in many situations, the internal camera calibration is unavailable. And moreover, we are often working with wide field of view cameras that can be calibrated in advance. Such cameras are very popular nowadays, and they have many advantages. For example, more stable pose estimates, the ability to observe a larger region of space, and therefore high robustness to occlusions or illumination. On the other hand, these cameras usually exhibit large lens distortion dominated by radial lens distortion. Ignoring the radial distortion may lead to significant errors in camera calibration or 3D reconstruction, like you can see on this image left, where the distortion is ignored and the reconstruction is not correct, compared to reconstruction where the distortion was estimated. One way how to deal with radial distortion is to pre-calibrate our cameras. This is unfortunately not always possible. Sometimes we are just working with collections of uncalibrated images downloaded from internet. Another possibility is to simply ignore distortion in the first phase and model it only in the final optimization step in the bundle adjustment. However, this approach is not very robust since it requires a set of correct image matches that need to cover a significant area of an image, including significantly distorted image points lying further from the distortion center. And it may be difficult to find such sets of correct image matches by using only pinhole camera model. Here you can see an example of for this behavior for the problem of image rectification with radial distortion. On the left, you can see the input image, and on in the top row, results of methods that ignore distortion in the first phase and model it only in the final optimization step. And as you can see, these rectifications are not correct. In the bottom row, you can see a result of our recent method for joint undistortion and rectification from coplanar repeats. And as you can see, this method works really well in this case. Here's another example of image stitching for cameras with different radial distortions. And again, as you can see on the right, only the method that was estimating 2 different radial distortions together with homography was able to correctly undistort these images compared to methods that were either not considering radial distortion or considering the same radial distortion in both images and later followed by some local optimization. So on these examples, you have seen that it is necessary to model the distortion when searching for an initial camera geometry model and inlier correspondences in the ransack loop. Radial distortion modeling has proven to be a mathematically challenging task, and algorithms for estimation of epipolar geometry, homography, or absolute camera pose together with radial distortion have been proposed only recently, especially after introduces Grabner-Bayes methods into computer vision community. Since the magnitude of radial distortion only depends on the distance of the image point from the center of distortion, it can be modeled in the following form, where XD is the original distorted image point, XU is the undistorted image point, XC is the center of distortion, and H is the function which defines the shape of the distortion model. In practice, the center of distortion is usually near the image center, which allows us to simplify this notation, this model. The nonlinear undistortion function H is usually approximated with a rational function. Here, mu I and lambda I are the parameters of the undistortion model, and R is the distance of the image point from the center of distortion. It is common to either only include nonlinear terms in the numerator, giving rise to very well-known polynomial models, or to use only the terms in the denominator, resulting in division models. Division models are often preferred over polynomial models as they require fewer terms to describe severe distortions more accurately. And one of the most popular models is the one-parameter division model that is used in most of the camera geometry solvers. This model provides a good trade-off between representation accuracy and model complexity, and it is usually sufficient to model most common cameras, including very popular GoPro cameras. In this model, the undistorted image point looks like this, where we have this undistortion parameter lambda. So now we can use this one-parameter division model in the estimation phase, and later in the bundle adjustment, we can use more complex model to bundle these parameters. Okay, so now that we have introduced the most common distortion models, let's look at solvers for camera geometry estimation under radial distortion. I will start with the relative pose solvers. So assuming this one-parameter division model, the well-known epipolar constraint results in cubic equations in 10 unknowns, 9 for the unknown fundamental matrix F, plus our undistortion parameter lambda. In this case, we have 8 degrees of freedom and more complex nonlinear equations than in the well-known 7-point solver for pinhole images. In the 7-point solver, epipolar constraint results in linear equations, and the final solver only solves 1 degree 3 equation in one unknown coming from this determinant constraint. The first solution to the simultaneous estimation of epipolar geometry and one-parameter division model was proposed already in 2001. However, this solver ignores the determinant constraint and therefore uses a non-minimal number of 9-point correspondences. In this formulation, the problem can be transformed into a quadratic eigenvalue problem with 10 solutions. The first minimal solution from 8-point correspondences was proposed much later in 2007, and the mentioned polynomial system, nonlinear system, is solved using the Grabner-Bayes method. This solution was later improved, for example, using the automatic generator of efficient polynomial Grabner-Bayes solvers, and this final solver performs Gaussian elimination of a matrix of this size 32 times 48, followed by some eigen decomposition of a matrix 16 times 16. This automatic generator that we proposed in 2008 opened the door to solving more complex problems, more complex systems of polynomial equations really efficiently. And this generator, together with the Grabner-Bayes method, was later used to solve many problems of joint estimation of camera geometry and radial distortion. For example, the problem of epipolar geometry for uncalibrated cameras with different radial distortions. As you can see, based on the size of the solver, this problem is much more complicated than the problem for camera with common radial distortion. In the literature, there are many variants of relative pose problem with radial distortion. For example, problems for one calibrated and one uncalibrated camera. However, I will not go into details here, since Magnus Oscarsson will later present a paper, a nice paper on this topic that summarizes all these relative pose solvers and proposes new and interesting solutions. Some of these new solvers are already very efficient, but some of them still result in complex systems of polynomial equations and complex solvers that are too slow for real-time applications. For example, the 9-point problem for uncalibrated cameras with different radial distortion is still quite slow. This problem is of particular interest, for example, for structure from motion from internet photo collections. Unfortunately, all existing minimal solutions are not suitable for real-time applications, and they are too slow for scaling to large data sets. Moreover, they are quite numerically unstable. And this motivated us to propose a non-minimal solution that uses only one more point, and that after manipulating of the input equations results in a polynomial of degree 10 in one unknown, and such polynomial can be efficiently solved using Sturm sequences, and the final solver is really stable and very fast, and it runs around 4 microseconds. Here you can see some results of this solver. On the left, you can see the input images followed by corrected images. And as you can see from this table, this 10-point solver, last row, is more than 1,000 times faster than the original minimal solver generated using this automatic generator. And it is also more stable. Here you can see another application where you can see 3D reconstruction from GoPro images with different radial distortions. This 3D reconstruction was created in Reality Capture, 3D reconstruction software from capturing reality, where this solver was incorporated. This solver is quite popular. If the cameras are observing a planar scene or undergo pure rotation, the geometry can be described by homography. In this case, each point correspondence gives 2 constraints. And since we have 9 degrees of freedom, 4.5 point correspondences are required to solve this problem. The first solution based on 5-point correspondences was proposed in 2001, and it again leads to a quadratic eigenvalue problem with 18 solutions. However, 5-point correspondences can also be used to estimate the homography between 2 cameras with different radial distortions. And in 2015, we proposed 2 efficient solvers for this problem, one minimal and one non-minimal. And these solvers run 1 to 3 microseconds, so they are really fast and easy to implement. Okay, so now let's move to another group of problems. Another group of important camera geometry problems are absolute pose problems. In this case, we want to estimate the position of and orientation of a camera with respect to a non-3D scene from 2D to 3D point correspondences. Such problems have applications in 3D reconstruction, visual localization. These problems or solvers are core components of these pipelines. They have application also in augmented reality or autonomous driving. In this case, the projection equation for an uncalibrated camera with unknown radial distortion and unknown focal length has the following form, where R and C are the unknown rotation and translation, F is the unknown focal length, lambda is our undistortion parameter, alpha I is the depth of the point xi. In this case, we have 8 degrees of freedom, and each correspondence gives us 2 constraints, so we need 4-point correspondences to solve this problem. And this problem was first solved in 2009 using the Grabner basis method. And however, the final solver was extremely slow and huge, and it was performing Gaussian elimination of a matrix with more than 1,000 rows. And since then, the problem was revisited several times. And in 2017, we proposed a solution based on the elimination ideal method, where we cleverly eliminated some unknowns. And the final solver performs Gaussian elimination of a quite small matrix, in this case, 40 times 50 matrix. Still, this solution is not the best for real-time applications. However, in 2013, we proposed another solution that uses 5-point correspondences instead of 4-point correspondences, so 1 more point. And this solution uses very nice 2-step approach based on so-called 1D radial cameras. This is really nice because here we can first estimate pose up to an unknown translation along principal axis. And then we can jointly solve for the translational degree of freedom, focal length, and up to 3 distortion parameters by solving a simple linear system. So the final solver is extremely efficient, stable. The runtime is less than 2 microseconds, and this solver is really popular in many applications. The solver inside RunSack is more efficient than the 4-point solver for a large range of outlier ratios, since it is much faster. Recently, we extended this 2-step approach based on 1D radial cameras to rational models of arbitrary degree for both distortion and undistortion. Distortion models allow for easier computation of reprojection errors in image space than undistortion models that were used in all previous minimal solvers. And therefore, they are useful for structure from motion augmented reality pipelines, where we need to compute these reprojection errors in this image space. In 2017, we used the same 2-step approach to solve also the absolute pose problem for a camera with unknown focal and radial distortion and principal point. And with this solver, we can register cropped images downloaded from internet, like these images here, for example, this image of a bag with Notre Dame picture. Okay, however, nowadays, almost all cameras are equipped with rolling shutter since they are cheaper and easier to manufacture. Rolling shutter sensors capture images line by line, leading to distortions when the camera moves or scene moves during the image capture. In this case, each line is potentially captured from a different pose, and therefore the final projection is not a perspective one, and it has to be modeled with more using a more complex geometry. So since the rolling shutter cameras capture each row at different time and potentially from a different pose, the camera rotation and translation are functions of the image row, and our equations are much more complicated. Rolling shutter projection, even after some simplifications like linear approximation of the camera rotation, the motion during image capture, and also linear approximation to the initial camera orientation, results in quite complex system of polynomial equations that is not solvable using algebraic methods like Grobner basis method. However, in 2020, we proposed a solution where we combine an iterative scheme with fast algebraic solvers for simple and tractable systems of polynomial equations. And here, the final solver is really simple and fast, and it usually converges in 10 iterations. And in each iteration, it solves a simple system of polynomial equations using Grobner basis method. And one iteration runs something like 40 microseconds. This solver outperforms the only existing competitive solution, which first calibrates the camera using a global shutter solver, and then uses a calibrated rolling shutter solver plus some local optimization. And as you can see in these tables, our solver returns more inlier, smaller focal length errors than this baseline. Our solver is the last column compared to the first two solvers, two columns. Here is also one example of an input image and undistorted corrected images using our solver on the right and this baseline. So in the last minute, I will show you nice results from one more problem. So the problem of image rectification with radial distortion. So the goal of rectification is to generate a frontoparallel view of the image scene plane. In this case, in our solvers, we are using only the imaged coplanar repeats. Coplanar repeats are regions that can be mapped to each other by planar Euclidean transformations. Image rectification has many applications, for example, single view 3D reconstruction, camera calibration, localization, or image editing. So recently we proposed two groups of minimal solvers, first minimal solvers to this problem of joint undistortion and affine rectification of distorted images of a scene plane from image translated and rigidly transformed coplanar repeats. In our solvers, coplanar repeats are represented by 3 points extracted from affine covariant features. And this is really nice because, for example, for coplanar repeats that are only translated, we only need to sample one feature correspondence to estimate the rectification radial distortion together with radial distortion. And this is really efficient inside RANSAC. And here you can see some results for different types of camera. On the top, you can see the original images, then undistorted images, and finally the rectified images using our solvers. If the coplanar repeats are rigidly transformed, so in the more general case, we are using a geometric invariant that coplanar repeats have the same scale in the rectified space. Here, the equations are much more complex, and we are solving them using Grobner basis method. And here are some nice results. Again, original images, then undistorted images. So I will zoom in to this undistorted image to see that this undistortion is really nice, and the rectified cutouts. So again, you can see nice rectifications. And note that our approach can recover details even under strong perspective distortions, as you can maybe see in this first image, where you can see in this rectified image this circular pattern that is barely visible in the input image. Actually, I didn't see that circular pattern there, and I was very surprised when I first saw this rectification that there is something like this, some circular pattern. And even though we are only using the one parameter division model, our solvers can handle severe radial distortions like this. Of course, now the rectification is not perfect, but I think it's still reasonable. Okay, so to conclude, hopefully this presentation convinced you that modeling radial distortion during the geometry estimation process is really important. There are solvers for many important camera geometry problems with radial distortion. However, they are not widely used, and I think it's probably because early solvers were rather inefficient, and efficient solvers are sometimes hidden in papers proposing general methods for improving the efficiency of minimal solvers, but hopefully this presentation will help you to find such solutions. Moreover, for some problems and settings, non-minimal solvers like minimal +1 solvers are preferable since they are much faster than minimal solvers and more useful in RANSAC. So in conclusion, I think solvers for estimating radial distortion together with camera geometry really unlock the full potential of wide field of view cameras, and they are really important for structure for motion or localization pipelines. So thank you very much.
Yeah, thank you for a great talk. So I think the live stream is a little behind, so start with one question. So as you already pointed out, right, so these solvers are beneficial, but still you're needing to sample one more sample. So do you have a feel of like for when that becomes, I mean, what low inlier rates that becomes much less efficient and it's maybe not worth anymore doing it? I mean, particularly
you mean something one more point? You mean something one more point? Yes. Yes, yeah, like so, it depends on the problem. Like sometimes one more point can significantly simplify your system of equations, and sometimes one more point will not help you at all. For example, for this rolling shutter problem, I was trying to derive such non-minimal solution for uncalibrated cameras with radial distortion and rolling shutter. And even after adding one or two more points, this system was still too complex to be solved somehow efficiently. And it really requires, like, you really need to have some feeling how to play with these equations. And as I said, like sometimes one more point can really help. And especially I think for relative and absolute pose solvers, it's really helpful. And I know that these solvers are preferable and they are used in, for example, in this structure for motion pipelines. I think there is no general answer like to this. Of course, also minimal solvers are developing and improving because we are still improving these methods for solving these systems of polynomial equations. So since they are more efficient, we can improve. For example, for this relative pose or absolute pose solver, the first solution was extremely slow, and only recently we proposed a solution using some recent techniques for eliminating unknowns that is reasonably fast. So it's much, like maybe 20 times faster than the previous solution. So I think this will change maybe after, like, the gap where I would suggest you to use non-minimal versus minimal for which, for example, outlier contaminations. This will also change over time based on how these methods will be maybe developing and improving.
I think they're pretty important, especially like for some of the more recent wide angle or wide field of view cameras and cell phones. I mean, I assume they are much more impactful than for zoom images.
Yes.
Thank you. So in the just saying this, like, if you have questions and you're listening, please ask them in the chat on YouTube so that we can see them, and Susanna can answer them.
Yeah, so in the meantime, I can have one question. So thank you for the talk. So my question is, I would think that this would be very useful for self-calibration procedure. Do you have any suggestions, what kind of motion or any set of things that you suggest if we want to use the solvers for self-calibration purpose, to avoid some degeneracy or to avoid some mismatch, especially in the very large distortion situations? I would assume that the feature matching might not give you very reliable initial matching locations.
Like, of course, it depends if whether you want to, for example, use just one image, if you want to do auto calibration for from a single image, or you want to you can take several pictures. Of course, you want to if you are using several pictures, you want to avoid some degeneracies, like some pure translational motion, or you can of course use these motions, and you can even derive much simpler solvers. Like you don't need to then use these general solvers if you know that you will do this self calibration, for example, for moving cars, and you know that you want to every now and then auto calibrate your camera because the calibration was corrupted, like the initial calibration, and you want to do this, and you know that your car is, for example, undergoing like pure translational motion, or you can approximate it with pure translational motion, and the rotation component is very small, or you can use some linearization of rotation, then you can derive a special solver just for this type of motion. And, of course, such solvers will be even more efficient than these general solvers that I showed here. And there are such solvers, and I think it, of course, as I said, like it depends on your application. What do you want? In which scenario you want to calibrate your camera? If you, for example, have a scene where you have man-made environment and you have these coplanar repeats, you can even calibrate it from a really like image of such scene with this coplanar repeats, single image, and this calibration works really nice. So hope this answered your question.
Yeah, thank you.
So one last quick question from the audience was, is there a C++ toolbox to leverage some of the great work you've been doing that people can look at?
Some of these solvers, like this is this is like some disadvantage that some of these solvers were not really implemented, or not really implemented, because we were proposing these solutions in these papers where we were proposing some methods for improving, general methods for improving minimal solvers, and we only derived some MATLAB implementation and sizes of these solvers. But the most interesting and most useful solvers are implemented in C++ very efficiently. For example, in POSLib library from Victor Larsson, you can find some of these solvers. And hopefully, soon I will create some list of all these different solvers together with some implementations with the help of my student, and hopefully all of these solvers will be available in C++. But the most interesting solvers are available. You can download them, for example, from this POSLib library from Victor Larsson.
Great. Thank you. Thanks for coming and giving the talk.
Yes, thank you very much. Stop sharing.
Okay, so now let me introduce our next keynote speaker, Professor Derek Hoyne.
Hello.
Hi, Derek. So Professor Hoyne is currently at UIUC. His research focused on general purpose vision systems that can adapt to solve a range of tasks in mixed view geometry that combines ideas from single view and multi-view geometries for structured 3D scene prediction. His work has been recognized with awards including ACM Doctoral Dissertation Award, Honorable Mention, CVPR Best Paper Award, PAMI Significant Young Researcher Award, etc. He's also a co-founder and CTO of Reconstruct, the company, which provides a modern beam solution which visually documents construction sites, matching images to plans and analyzing productivity and risks for delay. So without further ado, welcome, Derek.
Okay, thank you. Thank you for having me here, and thank you for the introduction. Yes, so I am going, this talk is more motivated by my work at Reconstruct, but I kind of have the dual perspectives of thinking of these problems from a research perspective as well as from a practice perspective. And so I want to talk about some of the, I think construction is a really important application area for 360 cameras and really for all cameras. And so I want to talk about some of those applications and challenges. So I think construction has an enormous potential for impact. There's many different areas. So one is, it has very low productivity growth. Economists calls it the least efficient industry. It hasn't had the same benefit yet from technology that many other industries have had. And in part, that's because of some of the technical challenges of deploying and integrating the technology into construction processes. 20 to 25% of the waste is failures in coordination. And that's pretty amazing considering it's a $1.2 trillion industry in the US. That's about $300 billion a year that's lost due to failures in coordination. This can be addressed through better, more timely, and more complete construction monitoring with the use of vision. Projects are often late and over budget. This impacts owners, construction teams, subcontractors. And so there's a lot of incentive to adopt technologies that can make a real difference. Construction accounts for 21% of work fatalities, including 1,000 deaths in 2018 alone. So again, safety is a big issue. Again, vision can help with that. And there's a shortage of skilled labor. So any improvements in efficiency that we can create through computer vision and other technologies in construction will not cost anybody jobs, but will allow more projects to move forward. On the other hand, construction sites increasingly use digital plans and schedules, which makes it much easier to incorporate other kinds of AI technologies. And the new generation of leaders in construction is tech friendly. Now, so there's a lot of problems to be solved in construction, and visual documentation are a key part of the overall solution. And again, there's many ways in which it can apply. So one is in visual documentation, where you want to create either 3D models or organized photos of the job site so that all the stakeholders can understand what's being done. This can also be used for after the fact documentation in case there's a problem. If you can integrate this with building information models and drawings and other design documents, then you can perform quality inspection. You can potentially identify problems much earlier. So for example, if a load-bearing beam is in the wrong place, you want to detect that before the structure that's supporting collapses. Detecting these problems earlier can prevent millions of dollars of rework and delays in projects. For safety, just having an overall model of the site can be very useful to communicate more effectively with the team. For example, don't work in this area because there's a crane will be operating low in that area. It's a dangerous area to work in. As well as things like detecting when you have missing toe boards and other safety issues that are kind of in the intermediate infrastructure of the job site. And then if you can integrate the visual documentation with schedule information, then you can do progress tracking and scheduling to help coordinate and streamline the workflow of the project to keep the project on time. So visual documentation is extremely important. Within that, 360 photos and video provide the most complete visual documentation. So construction's a huge application area. Vision is a huge part of the solution to construction. 360 photos and video are an essential part of that computer vision solution. And so that's why the reason is just that, especially indoors, you care about the ceilings, you care about the floor, you care about all the walls. You want to capture every single surface in the environment so that you can identify defects, so that you can tell whether things have been installed, so that you can detect safety issues. So it's not just a nice to have, you need to have this complete 360 capture. And that's why most of the construction technology companies that involve vision, especially doing interiors, use 360 video or cameras and have their solutions built around that method of capture. So I'll give you some more detailed examples within Reconstruct, and then I will talk about some of the technical challenges in creating these solutions, some of which are very specific to 360 and some are more general problems. So Reconstruct basically brings together what we call reality capture. So photos from 360 cameras, from drones, from crane cameras, from smartphones, together with building information models and plans that tell you where things should be constructed and provide other information about those elements, and schedules, which tell you when things should be constructed and who's going to be doing it. So by integrating the reality, the as-built, with the plans and schedule, we can say what is there versus what should be there, both in terms of are things installed in the correct place, as well as how is the project doing schedule-wise? Are we on time according to the latest weekly work plan, according to the master schedule, and so on? So here's a more detailed example of that in practice. This is a train station in Japan where somebody just walks through the site holding a 360 camera above their head. It's a video camera. Reconstruct, creates a 3D model from that, localizes all the frames, creates this like virtual tour. And because there's an underlying 3D model, you can then like perform measurements and you can do earth filling, volumetric measurements, area measurements, linear measurements, and so on, to be able to perform some quick quality checks. In this example, we also have a building information model. So it's a 3D model of where elements should be constructed. And so because we can align the reality model, the photos and point clouds to the building plans, we can then overlay all of the design elements on top of the photos or on top of the 3D model that we create. So you can see where the pipes were installed. You can see where all the different ductwork and beams and things should have been installed. And so then you can verify that the site was correctly built. And this can be extremely helpful even on visual inspection to quickly identify problems before they propagate to later stages of the construction. And here's one more example. You can also organize the photos and videos and point clouds on a drawing. Construction teams are mostly drawing based. They're more familiar with working with drawings and building information models. But we can automatically align to the drawings. Then you can do this same kind of virtual tour, BIM overlay and stuff, and you have the drawing as a reference. And then finally, if you can register your photos, create 3D models, align to plans, and you have schedule as well, then you can monitor progress, meaning identify like what stage, how complete different tasks are, and aggregate to create reports of progress of the entire project. And so this would involve in the images, recognizing building elements like ducts and walls, as well as identifying the stage of construction. For example, in walls, you would go through framing, insulation, hang the drywall, tape, plaster, paint, maybe put a facade on. And so then you can recognize those in the images. Then we have an underlying like 3D model as a basis that can be used to aggregate this information and compare to the building plans. So, and then all of this like ties into the whole construction process. So here's, previously these meetings would basically be people looking at sheets of paper that would have like location IDs and kind of abstract ways of describing the site that are hard to remember and lead to failures in coordination. Having all of these visual components and insights from the visual capture is extremely useful for coordination and communication. So there's a lot of so like 360 cameras have like this enormous like $100 billion application area in construction, but there's a lot of problems to overcome as well. One of the problems is just the camera image quality is not quite as good for consumer 360 cameras as it is for other consumer cameras or DSLR cameras. And while there are like very high-end 360 cameras, they're often not really usable on job sites. One reason is the cost. The other is that they tend to produce extremely large images. They're made for like entertainment, and they're not really useful for this kind of like rough and ready workflow where you want to do the capture really quick. You do it on a daily or weekly basis. You want things to upload quickly. Your job is not to do the capture. The capture is like part of a tool that you use to help manage the site. So a lot of the really high-grade professional 360 cameras don't apply, and the consumer ones have problems of low resolution, even if they're like 5K. When you look at a single part of the 360 image, it's pretty low res, noisy, blurry. There's also high sensor noise, pure low light quality compared to what you would see in an iPhone or something that has a lot of smart algorithms and really high quality sensors. This is a problem, especially in construction, because the building's not built, so they don't have all the lights installed necessarily, and it can be hard to like bring all the lights with you. Even below, in the image below, this is even captured, it's during daytime, so there should be plenty of light coming in since the walls are not constructed yet. But still the low light is resulting in or not even low light, but shaded light is causing, very poor quality, which impacts the reconstruction. Also, a lot of cameras have geometric distortion problems if you're working directly from the 360 images, and that can cause failures in reconstruction if you assume that the equirectangular image is like perfectly modeled by like a spherical projection. But it can still be helpful to use that model because some of the cameras like the Insta360 have very good stitching algorithms that would be difficult to otherwise replicate. And then finally, the file sizes are big, in part because you're covering a large range of angles, but also I think the compression algorithms that are so effective for perspective images are not as well tuned for the 360 images and video, but usually the same compression algorithms are applied. So then there's also a bunch of many goals and challenges on the algorithm side of computer vision and use of 360 images within this application space. And so I want to go through them one by one. This is an outline. So in the project, what happens is that you first get 360 images of the site. This could be in the form of a video or of still images. And the first thing you need to do in order to do any kind of further analysis or produce any deliverables is to register the 360 images to each other so that you know their relative positions. And here I think the big challenge is in the feature extraction and matching. The features that, have been extremely well studied for perspective images. SIF still works quite well. But for applying the same features directly on rectangular images would not work that well. There have been some methods to apply directly to equirectangular images, but then often the efficiency is not quite as good. And still you have still I think they're not as well tuned as the more traditional features. You can unwarp your images, but depending on how you unwarp, you would get different results. And there's still, again, if you're trying to make it be extremely efficient, as well as get very reliable matching, there's a lot of challenges that still need to be addressed. Once you have the registered photos, then you can do a photo tour to jump between the 360 photos. And there the challenge is how to transition seamlessly. And you need to have like a accurate, but it doesn't need to be very precise, but you need to have a very accurate 3D model that can be used as the basis of texture mapping in order to do novel view synthesis. That's one approach, but creating those models is challenging in these complex scenes. Given the registered images, you can next create a 3D reality model using multi-view stereo and 3D modeling. I think there the big technical challenge is to integrate the complete and structured 3D scene information that we can get from single view information with the precise but unstructured and incomplete depth information that we get from multi-view stereo. And I think that this problem of integrating single view and multi-view reconstruction applies much more generally than construction. Once you have a reality model, then we can create other views like a floor map that can be used to help understand the space better. And there the challenge is robustness to occlusion and geometric artifacts, that like the camera person that holds the 360 camera is always going to be in frame. And so they're not reconstructed geometrically. So you still need your mapping method to be robust to those occlusions, for example. Then you have to align the reality model to the building plans. That has different challenges. If you're aligning directly from your 3D point cloud to the building plans, the problem is that the plans are abstract. They don't account for a lot of the things that are in the scene. They're also based on a completed building where this building is actually in progress. So a lot of the walls may not have been built yet, for example. And further, the person doing the capture, the capture may only be of a small portion of what's shown on a drawing. If you're aligning between point clouds or from image to image, the challenge is that, again, you may have a partial capture and the site conditions are quickly changing. So a lot of appearances will change. And then if you've got all of this, then we can do recognition. There, the challenge is to do robust recognition from many viewpoints when you have some information about the underlying geometry. I think that's more, it creates a lot of opportunities that are not studied in most image-based recognition work. And then finally, if we have if we've recognized the elements and we have aligned models to plans, then we can create visually documented reports of progress and quality. And one of the extra challenges there is that we need to differentiate between not observing an element and knowing that it's not there. So like if on the site they install piping and then put up the drywall before the next capture, we need to say that we didn't observe the pipes rather than that they're not installed. So to conclude, 360 cameras are a crucial tool for construction. They're such important applications. I think one of the most important application areas of computer vision. But there's still a lot of research needed, both on the hardware side to improve the quality of the images, of the stitching, as well as to reduce file sizes. And on the algorithm side, there's a variety of challenges in terms of registration, reconstruction, and recognition. Thank you.
Well, thank you so much, Derek. I see already a question from YouTube. So one person asked, a lot of environments are featureless, like drywalls. How do you handle them?
Yeah, that's a good question. So this is one of the areas where like combining kind of like the recognition-based geometry approaches and the multi-view stereo-based geometry approaches can help. I can't like give all the details, but we can we take an approach that tries to leverage the multi-view stereo to create like a framework for recognition, and then we can fill in a lot of the gaps using recognition-based methods.
What do you think? Just follow up. So, what do you think about like a room layout type of network-based?
Yeah, I think it's really interesting, but hard to know exactly how to apply it. And I've done work myself on predicting indoor scene layout from 360 images. The problem is that the layouts of construction sites, like you can see on the top there, are pretty complicated. So like a lot of times these indoor layout algorithms are made for finished like simple rooms. But I think that there's a lot of important, I think that there's a solution. I just don't know exactly what the solution is. The problem is the challenge is to use that structure that you get from the view-based like layout estimation as a guide or as a way to like fill in the gaps of the result that you would get from multi-view stereo.
Mark is asking also, can you elaborate a little bit perhaps on the failure of feature matching when computed on undistorted projection of the images?
Yeah, so So I would say, like, I mean, overall it works. I think that there's a lot of room for improvement. One of the things is, so like one approach that you can take is you can undistort the 360 image into like 6 perspective views, for example, corresponding to the cube. Depending on how you orient that cube, you're going to get different perspective images. And if you do it differently for different if the way you do it isn't like consistent across the 360 images in their like stored poses, then you can have like perspective problems in your feature matching. The other problem is just that the efficiency of the time that it takes to compute to undistort, compute the features, and do the registration or do the matching on the entire 360 images is a lot greater than the time that it takes for like perspective images. So I think there's also, it's partly an efficiency issue.
Right, in terms of capturing, it's much faster, definitely. So the other thing is that how one question asking, how can you ensure that your customer is capturing enough data for you? I think
that's a good question. So that's like one reason that 360 is so nice is that at least it guarantees that every image covers everything, and like nearby images will have a lot of overlap since they cover all views. And so earlier on, we tried solutions using regular video, and that was not that was like extremely difficult to capture enough. So our first solution using 360, we always required video because that would guarantee that there was a lot of frames. So then like we don't have to provide any special instruction. And we currently use either video or like a time lapse where we just sample images frequently. So it's basically just by frequently sampling the images and using 360, that capture process is much easier than it would be if we were using perspective cameras, like what you would use with drones or handheld cameras or or like phones.
Well, due to time, thank you, Derek, again, and thank you for coming to give us a talk. Very nice.
You're very welcome. Thanks.
Yeah.
So, yeah.
Thank you, Derek and Susanna. And we're moving on to the orals of the session. So the first oral is called Panel DRs, Spherical Panorama Diminished Reality for Indoor Scenes. The talk will be given by Vasilios Gistas from the Center of Research and Technology, Helenas, Thessaloniki, Greece. With that, please get started.
Hello, everyone. Hello, everyone. Can you hear me?
Yeah. Yes, we can.
Yeah. So I am Vasilios Gitsas, and I will present on behalf of Visual Computing Lab our work PanoDR, diminished reality for indoor spherical panoramas. Firstly, we will try to address the question what diminished reality is. It is the process of removing objects that exist in our visual perception by replacing them with content that preserves the structural coherency and photorealism. Another question is why and when should we use diminished reality? There are multiple reasons for that. One of the reasons is the rising availability of commercial 360 cameras, along with the increasing demand for novel applications concerning interior space redecoration. And next, the huge interest in emerging technologies, namely AR, which can be further enhanced by diminished reality. As we all know, furniture retailers have already developed such AR applications. Among image synthesis techniques, imaging painting can be used in diminished reality settings. Imaging painting seeks to fill missing regions of an image, and current state-of-the-art works produce high-quality results, even on extremely large holes. Nevertheless, it focuses only on photorealism and not to preserve the structure of the occluded areas. Another image synthesis approach, image-to-image translation, aims to transfer an image from one domain to another while maintaining the input structure. This approach can facilitate diminished reality in terms of boundary preservation. Nonetheless, it cannot be directly used for DR. The big question is if the aforementioned methods can actually solve the DR problem. In order to ask those questions, we need to take into consideration the following points for our case. First, the inherent ambiguity of hallucinating occluded areas. Second, the fact that the surrounding context should be taken into account in order to fill the whole. Image-to-image translation solves the first one, while imaging painting manages to solve the latter. Our goal is to approach the DR task by translating a full image to an empty one. Thus, we leverage the recent advantages in image-to-image translation and imaging painting. Now, I shall describe our method, which basically aims to bridge the two worlds. Firstly, the object to be diminished in the input panorama is masked. Afterward, we feed the masked image to the surrounding context encoder. Its architecture is derived from imaging painting and it relies on gated convolution and repeated dilations. The encoded representation is then fed to the structure-aware decoder. Stemming from the fact that wall, floor, and ceiling depict the occluded structure of an indoor scene, we use a pre-trained layout segmentation model to estimate it. In order to facilitate our network with the structural information, we employ two scene residual blocks in the decoder. In addition, per region style codes are computed by a style encoder for the input image. As far as concerns the scene normalization, the style codes go through a per style convolution and then are scattered to their corresponding region based on their dense layout map. The generated style map, along with the dense layout, are passed through two separate convolution layers in order to learn two sets of modulation parameters. In this way, we provide a structural guidance to our model in order to maintain the structural coherency of the scene while controlling the style of the hallucinated content. Therefore, we're learning a mapping from a fully furnished to an empty background-only scene, conditioned in its structure and per structure class style. After generating the predicted background-only image, we composite it with the input image and obtain the diminished one. In order to supervise our model, first we employ a low-level reconstruction loss, composed of a spherical weighted L1 loss and the total variation smoothness prior. In addition, we employ a high-level synthesis loss comprised of perceptual and style losses. Last but not least, we employ an adaptive adversarial loss, which encompasses a hit gun loss and a feature matching loss in the discriminator's intermediate features. In order to supervise our model for each input scene, the corresponding empty one should be available. All byte stashing configuration is provided by the restructured 3D dataset. The photometric inconsistency between empty and full rooms can be noticed in the second column. This is due to ray tracing rendering that affects the global illumination and texture. The diminished area in the second column clearly indicates that this inconsistency is severe, a fact that hinders the applicability of the dataset for supervised learning-based methods. In order to tackle this shortcoming, we augment empty scenes with objects from the full scenes. It is apparent in the diminished object region in the third column that we overcome the photometric inconsistency in the diminished area. Let's move now on some qualitative results of our method. We see some samples from the structured 3D testset. It can be seen that our method preserves the scene structure while generates the photorealistic content. Regarding the quantitative results, we compared our method with two state-of-the-art imaging painting methods. Our method is likely to generate smoother results, a fact that is reflected through the per pixel and pixel neighborhood-based metrics. For example, for this scene, assume that we want to diminish the highlighted closet. The diminished image obtained from the compared method exhibits some flaws, both in structure and texture. On the contrary, our method captures the scene structure while the texture details are satisfying given the demandingness of the scene. Given the generative nature of our task, we consider LPIPs as an important metric since it assesses the perceptual similarity between the two images. Again, the bar chart clearly indicates that our model outperforms the compared methods. For instance, assume that we are given this challenging scene and the object to be diminished. It can be seen that the compared method generates artifacts, whereas our method generates content that is reasonable in terms of structure and texture. Finally, we measure the MIOU between ground truth and diminished results to assess the boundary preservation. The evaluation is focused on the segmentation results inside the mask region. As seen in the example, the prediction from RFR model misses to capture the boundary of the scene structure. In contrast, our method is able to capture the boundary with detail. Interestingly, our approach exhibits significantly faster convergence. A glance at the bar charts reveals that our model needs only 60 epochs to converge. This is attributed to the interaction between the scene residual blocks and the discriminator. By explicitly guiding the model to generate plausible structure through scene blocks, the discriminator focuses from the early training on the texture details. Thus, combined with the low-level and high-level losses, our model converges faster to high-quality results. Further, we have addressed some drawbacks which are to be tackled in our future work. Firstly, our training data are synthetic. Thus, our model is not proper for inference on real data, as can be seen in the following in the wild diminished scenes. In addition, the requirement for the pre-trained layout estimation model makes the training process complex. In conclusion, we showed that existing datasets do not provide the straightforward way to train models in diminished reality settings. We developed a hybrid imaging painting and image-to-image translation model for diminished reality, the first to our knowledge for 360 images. Last but not least, our approach not only surpasses the compared methods, but also exhibits significantly faster convergence. Thank you very much. For more info, you can refer to our project page and code.
Yeah. Thank you for a great talk. Very nice. I have a question. So do you have a feel on how much you rely on this wide field of view in the 360 images? Because you mentioned like augmented reality to replace stuff in your environment later. And so then often you wouldn't have as a large field of large of a field of view as in the 360 images. So would your message fairly straightforwardly translate to perspective images, or are you relying much on the field of view?
Well, generally, the first attempt to run this work was on perspective images. Because we have set up a technique that generally take a perspective image from its spherical panorama, but this for other reasons didn't keep up. So it's not bounded on a wide field of view, that's for sure.
Okay. Thank you.
Okay.
Yeah, thank you for your talk. I think we'll move on to the second presentation. Unfortunately, we don't have more time for questions, so hand it over to Lee.
Thank you very much.
Thank you. So our next talk is for fast solver for minimal radial distortion relative post problems. It's going to be presented by Magnus Oskarsson from Lund University, Sweden.
Yes. Let's. Okay, thank you. So I'm Magnus Oskarsson from Lund University. So I'm going to talk about fast solvers for minimal radial distortion relative pose problems. So thanks to Susanna, nice introduction. We've seen quite a lot of the background on these kinds of problems, but basically what we're looking at in this setting is that we have relative pose. So we have two views with a number of point correspondences, and we want to estimate the epipolar geometry. So we want to estimate the relative rotation and translation. But we're also interested in different cases of calibration. So we're looking at different cases of unknown and known focal length and different kinds of radial distortion. So we're in this paper, we modeled the radial distortion using the division model using one single parameter. So just to give an overview of what our main contributions in the papers are. So it's basically we present a common framework so that we can formulate a large class of different kinds of radial distortion relative pose problems within one general setting. So we can describe solvers for many types of similar problems. But we also present efficient implementations of this. So new fast minimal solvers for previously unsolved cases, and also fast solvers for previously known cases. And there was a question previously on the availability of code. So here we have implementations in MEX, C++, MATLAB versions of all these solvers. So just to give you some motivation on why you would like to look at many of these different kinds of radial distortion problems. So in structure for motion, for instance, from unordinary images, a very large and time-consuming part is doing the pairwise matching over images. So this is a typical bottleneck in any structure for motion pipeline, doing pairwise relative pose estimation for inlier estimation, basically. So what you can do is you can use keyframes. So this will definitely avoid the combinatorial explosion. And then using keyframes, you match a number of images to this keyframe. However, you would like this keyframe to cover quite a lot of field of view in order to be able to match several images to this keyframe. So one way of doing this is using a wide angle lens or a fisheye lens or something like that. But that gives rise to the need for different kinds of solvers here. So you could have different known calibrations in the images. So you can have known focal length, unknown focal length, and also you have asymmetric cases. So you have maybe one-sided radial distortion or two-sided with different kinds of radial distortion and so on. So that's sort of the motivation. So just to formulate the problem here, so I don't have time to go into that much detail, but I'll sort of outline exactly what we're talking about here. So the equation one here is the epipolar constraints here for the line correspondences. We have a minimal set typically, so 7 to 9 points typically. And we want to estimate F here, which is the fundamental matrix. And we're given point correspondences, and these are radially distorted through this function G here, which is linear in the lambda, which is the also unknown, typically radial distortion parameters. So the F here is the fundamental matrix, and we're looking at different kinds of calibration manifolds. So this could be an ordinary essential matrix when we have fully calibrated cameras. Then that would be the trace constraints. You could have completely unknown calibration, that would be just the ordinary fundamental matrix with just the determinant constraint, and then there are constraints in between these. So the equations 1 here are typically used to eliminate parameters, and then you insert them into the nonlinear constraints in 2. We saw this a bit previously also on Susanna's talk, that there are a number of these cases which have been solved. So this is sort of an overview of all the possible cases that you can have for 2-view given focal length, unknown focal length, and so on. So these are all the possible cases in that case. And a number of these have been solved previously, but we want to sort of give a common framework for all of these problems. So the main contribution here is that we formulate this in a bilinear formulation. So we're looking at the equations, the epipolar constraints, just looking at them as linear. That's the main point. They're all linear in F, the fundamental matrix parameters. And then we can look at them as functions of the radial distortion parameters. So what we do is we use all possible constraints here to eliminate as many parameters in F as possible. That will depend on the problem, how many you can do exactly. But previous solvers haven't exploited this bilinear structure in the sense that they have just eliminated some of the parameters. So we eliminate as many of the entries in F as possible, so that will lead to rational expressions in the radial parameters. So this will give fewer parameters in the nonlinear constraints, which we then use in our Grosvenor-Races methods with Sturm sequences to give efficient solvers. So these rational expressions can in some cases lead to spurious solutions, but these can often be handled at runtime using these Sturm sequences. But that is one caveat. So these are the state-of-the-art solvers here, and the template size here says something about the size of the speed of the solvers. That's the main time-consuming part in solvers. So this is our contribution, that we give in general faster solvers with smaller templates. In some cases we get a number more solutions, but since we're using Sturm sequences, it doesn't add that much problem in the final solution. Yes, and just to sort of wrap things up here, all the details about the solvers and the implementations, and also runtimes and numerical properties can be found in the paper, but I don't have time to go through that. So this is the typical use case here for a runsuck run here. So this is running our lambda FE solver. So we have the first camera, the left-hand camera, is fully calibrated with known focal length. The second camera is with unknown focal length and some radial distortion. So we estimate the lambda and the F, and this is the final inlier set for a quite difficult problem where we have a very large field of view and need to match many points here. Okay, that wraps my talk up. So thank you for your time.
Thank you so much, Manis. And so while we're waiting for online questions, let me start with this. So first of all, thank you so much for sharing the code as previously asked. This is going to be really helpful for us to try out. But so what's the next step that you're thinking in terms of minimum solvers? And any plans that?
I think that one thing that also Susanna mentioned is that these are quite difficult problems compared to the ordinary uncalibrated or the standard fully calibrated cases, and in some sense they are inherently a bit ill-posed also. So some of these solvers will have quite bad numerics. So there's still work in order to improve the numerics. That's one thing. They're quite fast, but the numerics can be quite shaky. That might not be a problem if you're running in a ransack setting. Typically, if you sort of get 10% failure cases, it's not a big problem. You can just sort of run more iterations. So that's typically what you would lose for bad numerics. But I would say that that's one point that there's still a lot of room for improvements on the numerical side.
So previously we mentioned about rolling shutters. So this one, does it consider anything or along that side or no?
No, this is just for the ordinary pinhole camera. So I think that, well, rolling shutter is also difficult. Then maybe you can maybe use combinations of other types of optimization maybe to handle those very nonlinear things which are difficult using this algebraic framework in general. I think that it's very difficult.
Got it. Thank you. I don't see any other questions on the web. So thank you again, Magnus.
Thank you.
Thank you for the talk. So I think we are at the end of our talks and our workshop, in fact. So let me share the last view of, yeah, let me share the last closing. Let's thank our keynote speakers and our authors and reviewers. More importantly, thanks for everyone coming to the workshop. But also I would like to take a little bit moment to thank all the organizers, my colleagues, Pierre, who is actually supporting the online streaming, where they have spent a lot of time try out to make sure that our streaming and workshop are working properly. And definitely Mark and other colleagues to start from the beginning of the second workshop, organizing and scheduling with the main conference coordinators, and also the very successful challenge that we have this year. And so far, I think we have enjoyed the conference. We have learned a lot, and there are a lot of things we can try out. Hopefully we can see you guys for the next workshop, and hopefully in person. I don't know if Jan has some more words to add up.
No, I mean, really thank you to all authors and speakers for making this a success, and Mark tirelessly organizing this with Pierre's help on making the online streaming work. Thank you.
Thank you. Thank you all for coming.